Linked list is a very popular data structure that has many applications, such as in building graphs, hash tables, LRU cache, and much more. But many people get confused when it comes to working with the internals of the linked list. Hi, my name is Pratik, and in this tutorial, I'll help you master the fundamental concepts of the linked list. But before we get started, make sure you check out free masterclasses on Scalar's event page from some of the best industry leading experts. The link is in the description below. Also, subscribe the channel if you haven't done already. Let's dive right in. Let us begin with linked list. What is a linked list? A linked list is a linear data structure in which the elements are represented as objects and they are stored in non-continuous memory locations. Okay. So one thing that you need to note about linked list is it's a dynamic data structure, right? So unlike an array where you need to tell, okay, I want an array of size n, you don't need to specify the size of the linked list. Every time you get a data, you create an object, you put the data inside it, and you put it in the form of a chain or in the form of a linked list, right? So why the name linked list? Because we have a lot of nodes. Okay, each node is an object in a heap, and these nodes are connected with each other, right? How they are connected? So each node is created at some memory. Let's say this address is 205. So the previous node knows that the next node is present at this address, right? So 2 will know the next node is present at some address, so that is also going to store there, right? So each node is going to store two things. One is your data and one is the address of next node, right? So if you know the address of next node, you can easily traverse the data structure and you can also put things in a ordered way, right? So every time you get a new data, we can insert at the beginning, we can insert at the end, we can also insert in the middle, right? So it's up to you how you want to maintain the ordering inside the linked list, right? One thing to note is it's a dynamic data structure, and the nodes in which the data is getting stored, they are stored in non-contiguous memory locations, unlike an array, right? So that is what linked list looks like, right? Now in linked list, we do not specify the size, as I have already discussed with you, and it is a dynamic data structure. It automatically changes size when an element is added or removed. So we'll go into the internals of how addition and deletions are performed on a linked list in this tutorial. So while doing the implementation, I will show you that, okay, if there is a node, how do I connect the next node? How do I add something in the beginning? How do I add something in the middle? How do I delete something, right? So the fundamental operations that we will be learning would be addition, okay, removal, right, and getting a node, right? So I want to get a particular node. I can, how do I get that node, right? So given an index, I can iterate to that index, right? One thing that is bad about linked list is if you suppose want to get the middle node, right? In array, you can say, okay, give me the ith element. So this property is called as random access. So linked list is a bad data structure if you need to access ith element. Why? Because you cannot directly get this element. You have to traverse till I positions to get this element, right? So it's bad at getting nodes. It's bad at random access, but it is good at certain things that we will see. All right. So that being said, let us jump into the implementation of linked list. So now let us dive into the implementation of linked list. So far, what we have learned is that linked list is a chain of nodes in which every node is connected to the next node. Okay. If there is a node 1, it must be connected to the second node, let's say node 2, right? The way to do it is that in every node, we also store the reference of the next node. Okay. For example, if this node is created at some memory location, let's say 206, then this node must store what is the reference of this node, where it is created, right? And for the first node, what we need to do, for example, if this node is created at some location 115, then we need to store this location 115 in a special variable. Okay, we generally call this special variable as head, right? Okay, and second node will store the reference to the third node and so on, right? So third node, maybe it might be at 480, so I might be storing 480 here, right? Now the first step in the implementation is that how do we implement this structure, okay, this object that we see here. So we are calling this object as a node object, right? What I will do, I will say, okay, I will define a node class, and this is capable of holding two things. One is my data and one is my reference, right? So each of these boxes is a node, right? So each node is going to hold a data. Now a data can be of a different type as well. So just for the sake of simplicity, I'm treating it to be a integer, but it can be an image, it could be a book, it could be any object, right? And second thing I have is a reference to the next node, right? So how do we store a reference to the next node, right? So I say, okay, this will be of the type node, and let's call this variable as next, right? We have data and we have next. So if you're confused, I will explain you what is this concept. So let us first start with the code. Let us create this structure and let us try to understand that, okay, inside the node class, you can have an object reference which is holding the address of the next node, right? So let us go into IntelliJ, and I have created a package called linked list data structure, and here I'm going to create a Java class called as let's say node.java, right? Now it automatically creates a class for me, but it does not have data members. So how do I add data members? I can say, okay, I want data, and I also want something called as next. So that will be of the type node, right? Now this does not mean that there will be an object inside an object. No, this is only a way, this node, right? It's only a way to hold the address of the next node, right? So this is of the type object reference. I will tell you, right? And let me do one more thing. Let me add a constructor here as well. So you will see why we need a constructor. Let's do one thing. Let's create main, right? Let's create a linked list demo, another class in which I'm going to test my functionality. In this class, I will create my main method where I'm going to test my functionality, right? Let us create a node object. Guys, okay, node A, this is equal to new node. Right now, this no, this does not hold any data, right? So A is not going to contain any data. By default, the value of integer is 0, right? And next would be null, right? So what I can do, I can say, okay, a dot data equals to 5, a dot next equals to null. And if I say, okay, s out a dot data, what I'm going to get, let us see, right? So I'm getting this value as 5, which is absolutely correct, right? Now, why this is happening? Let's see. Right? So what it did, writing this code, it created a node, right? And what is A? A is referring to this node. So A is a address, right? A is a object reference. So A is another bucket which is holding the address of this node. So this node has two things. One is my data and one is my null. So this is your data and this is your next. And this node has been created at some memory location in the heap, right? This is my heap memory. Right? So a this address might be, let's say, 508, right? What is A holding? A is holding 508. This is what is exactly happening behind the scenes. So in this case, this A is also an object reference, right? And it is referring to an object. Inside that object, I have one more reference. Okay, how do I access this value? I access this value by a dot next. So this is what is happening when you are creating this node, right? So it is giving you, uh, it's wrapping up two data members inside one bucket. Inside node, you have an integer value and a reference to the next node, right? If I say, okay, there is one more node, right? Let's say node b equals to new node, right? And I say, okay, a dot next should refer to b. So if I print out what is a dot next, so a dot next is nothing but it is the address of the b node that we have created, or the value that is getting stored inside b, right? Now if you see, this is the reference of the next node, right? So let me show you through a memory diagram. So a is referring to a node, okay? So a is 5, b is some other node. So let me do it like this. So a is a variable that is holding this address, let's say 108. This value is 5, and b is 30c, right? So b is some other node. B is another variable that is holding this value 30c, right? And this is the address of next node. I don't have any data and null value here, so it will be the default value of integer and next, right? So that will be 0 and null, right? So I have 0 and I have null, right? Now b is referring to this. So when I say a dot next equal to b, so inside a dot next, which is this field, I'm copying whatever is present in b. So I'm copying 30c. So it means, in a way, this b got connected with a, right? Now even if I lose this variable b, this chain is still connected, right? So this is how we are going to work with nodes, and we will write one more class that does all this manipulation of nodes. Okay, we'll call that as a linked list class, right? So I hope this node concept is clear. What is a, what is new node? The new node is getting created in heap. In this case, this is a reference variable here, and this variable is created inside stack at this point, right? So what I will do, I'll remove all this code, and I will do one more thing. So instead of like every time doing a dot data equal to something, a dot next equal to something, I will define a constructor inside this class. So I call it as node. It will accept some integer, let's say data. It will accept some value of next, but in general we will not know that value of next. Okay, so whenever you creating a new node, you know the data. You say, okay, I want to create a new node with data 7. What will be connected in the next node, we do not know at the moment, right? So what we can do, we can leave this variable initialized with the default value, right? So I can say this dot data equals to data. So I'm initializing this variable with the data that I'm getting, right? So since the two variable names are same, writing this here is important so that compiler knows that we are talking about this data member as an attribute, right? And next, what about next? So you can say next is null, or you can say this dot next is null. Both are fine, both will work, right? So this is the constructor for the node class, right? Now if you want to create a node a, now you will say, okay, node a equals to new node. You just give the data as 5, and you say node b equal to new node. You say data is 6, and a dot next equal to b. This creates a very simple linked list in which we have two nodes. Okay, if I say s out a dot data and show me what is the data in the next of a. So how do I do it? A dot next gives me the address of b dot data. So I'll say 5 followed by 6, right? So I will see this. So I see 5 followed by 6. So what we did, we simply created a linked list in which we have just two nodes. This is a, this is b, right? Okay, and a dot next is storing b. So a dot next is storing, right? Now you might say, okay, this looks very easy, but if I have to add 10 nodes, 20 nodes, 100 nodes, 1000 nodes, will we create so many variables and attach them manually? The answer is of course no. We will write an algorithm that does insertion in the linked list, deletion in the linked list, and it helps me to get the nodes in the middle of the linked list, or at the end of the linked list, or at the beginning of the linked list, right? So to do all these operations, what we will be doing, we will be writing our own linked list class. So what I will do, I'll create a new Java class, and I will call it as linked list.java, in which all these operations involving these nodes will be done, right? Let's see the implementation of linked list. So let us see the implementation of linked list. Now suppose you want a data structure that is like in the form of a chain, right? And you want to build certain methods. You want to say, okay, I want to do addition in this linked list. That means I should be able to add more nodes inside it. I should be able to remove nodes from this linked list, and I should be able to get the nodes from this linked list. That means I want to read nodes from the linked list, right? Now the add operation, it can happen at three places, right? Maybe if there is a linked list like this, you can say, okay, I want to add something in the beginning of the linked list. So I can say, okay, add at the first position. Or you might say, okay, I want to add something after the last node, right? So you might say, okay, I want to add at the last node. Or I might want to say that I want to insert something in the middle. So I might be doing something in the middle or at a given location. Okay, at a given position inside this uh, linked list, right? Similarly, remove can happen at the beginning. So I will say remove first would be an operation, remove last would be an operation, and remove at a particular position can be an operation. Similarly, get means, okay, I want to read something. I want to get the first element, I want to get the last element, or I want to get the middle element, right? So I will say I want to get first element, last element, and element at a given position, right? So what we will be doing, we will be implementing these operations, right? Now in order to implement these operations, right, What is important? Let us start by understanding how my add operation will work, right? So whenever you want to add something, so one thing you need to know is what is the starting point of the linked list, right? So suppose you want to add something in the beginning, you must know the starting point, or you want to add something at the end, right? Now, one way is if you're adding something at the end, right? That means if you're creating a node here, you must access this node and update the next variable of this node, right? You would say, okay, in the ending of this node, I will attach this node. So one way is you always iterate till this point, starting from the head, and this will actually take order of n time. If you iterate from here to here, it will take order of n time. So I don't want to do that. What I will do, I will say, okay, every linked list will at least know what is my head and what is my tail. So I will keep another reference that always point to the last node of the linked list. Whenever you will add a new node at the ending of the linked list, I'll say, okay, I'll modify the tail node, I will attach the node, and I will update my tail variable to go here, right? So let us see how these operations are implemented. So what I'm trying to tell you is that if you're implementing a class called linked list, this linked list will have data members, okay, something that the linked list should know, okay, and some operations that the linked list will does, right? So here are the operations, they will be part of the methods, right? And we will have some data members or attributes. What are the data members? What are the things that the linked list must know? One is head. What is my starting address? One is the tail. What is my ending address? So again, keeping this is optional, but I want to optimize certain operations. For example, add at last should not be an order n operation, it should be an order one operation. So I need to keep the tail variable as well, right? And maybe some optional information like size, how many nodes I have in the linked list. Okay, so maybe I want to implement a method like get size, how many items are already inserted in this linked list. This is a useful operation. We want to check, okay, if the size is 0, that means linked list is empty, right? Otherwise, you can check if the head is null, that also means linked list is empty, right? So we will also implement this operation like get size, and maybe we'll implement operation like display. I want to show the entire linked list, okay? Or you can implement a method like toString, iterate on this linked list and convert it into a string. So that is just like a display method. I want to show the entire linked list to the user, right? So let us start by implementing these operations one by one. So this is my linked list class. So first of all, what I will do, I will add some data members and I will add a constructor to it. Else, okay, I want to create a head. So node head, right? Again, head is a object reference, hence it has a data type called as node, right? Then I will have node tail, and one thing I can do is I can make them private. So private node head and private node tail. I don't want people outside the linked list class to know where is the head node, where is the tail node. So I will not expose this data outside the linked list class, right? And I can also say private int size. I'm not making it public because I don't want this size to be changed by someone outside. The size should change automatically when something is inserted or something is removed from the linked list. So it should be a private variable only changed by the linked list class, right? Next thing I want to do is I need to initialize a constructor, okay? Whenever user says, okay, give me a new linked list, what should I do? That linked list will have 0 nodes inside it. So I need to initialize these three data members as well. Else, okay, linked list, there is a constructor here. And what I want to do, I want to say head and tail, they will be null and the size would be 0. Okay, so this is my constructor. Now, what is the first thing I will do? Else, okay, I want to do an insertion. So I'll write three methods. One to add something at the beginning, something at the end, and something at a given position in the linked list. That's okay. Public method, and the method is of the type void add, and let me call it as add first, and public void add last, and public void add at a particular position. So add. So in all the three methods, I should know what is the data that I need to add. And in the third method, I should also know at what index I need to add, right? Now take a pause and think, how you will implement these methods. Okay, if you're given a linked list and you want to add something at the beginning of the linked list, how you would add in. Okay, so what will be the code behind this method? Take a pause and think about it. Okay, so let us discuss the first method, add first. Now suppose you have a linked list, right? Let's say this is A, this is B, this is C. This is already there and head is referring to this node. I want to say, okay, I want to add another node D, which is at the beginning of the linked list, right? So how I will do it? So first thing is I need to create this node. So how do I create a node object? Very easy. I simply say, let me create a node called as N. This is equal to new node, and the data of this node is same as this data that I've given. So this creates a new node and N is referring to this node, right? N is a object reference, a local reference created inside this function, which is referring to this particular node. What should I do? How do I connect this? I would say, okay, N dot next should refer to the head. So if head is already there, N dot next should connect to head. So it makes this connection, right? One thing I need to do is I need to say, okay, this head, it should move here, right? This head should not refer to A, instead this head should refer to now D. So I can say head is equal to N. So this will work really well. And one more thing I will do is size plus plus. Every insertion will increment the size of the linked list, right? So this will work really well if the linked list is already there, right? But suppose you are creating the linked list for the first time and you call the add first method. So head and tail both were null, right? And you said, okay, I want to create a new node. So you created a new node called D, and n dot next is equal to head. So head was null, so D's next is also null, which is fine, right? And then you say head is equal to N. This head refers to this node, which is also fine, right? But the thing is, the tail is not getting updated, right? Whenever the first node is inserted, right? Let's say the first node is A, both head and tail should refer to this node, right? What I can do, I need to add a separate condition that if what if the size was 0 before adding this node, in that case my tail will also get updated. So tail should also point to head, or tail should also refer to n, right? Now this is a special case when you have 0 nodes. In that case you also need to update the tail, right? So this is my add first method. Now let us test the functionality of add first method. So what I will do, I will go in linked list demo. It's okay, I want to create a linked list. L, this is equal to new linked list. And now in this, I can say, okay, L dot add first, and I will give some data, let's say 10, and say L dot add first, I will add 20, and then L dot add first, I will add 30, right? So I want to see this linked list. So I will call the display method, which I have not implemented. So we will implement the display method as well, right? Let us go back into the linked list class and let us add one more method, public void display, right? So how do I display the linked list? Now it's going to be pretty easy. Suppose the linked list is 30 followed by 20 followed by 10, right? And head is referring to this node. Okay, tail is referring to this node. This is 10, right? So tail is referring to this node. So what I need to do, I need to start iterating from head till the end. So I'll say, okay, I'll take a temp variable, I will print it, and I will take temp here. I'll print it, I will take temp here. I'll print it, I will take temp here, right? So what is happening? So once my temp reaches null, I will stop. What I can do, I can say node temp, this is equal to null. So temp is again a reference, it's not a node, right? So sorry, it's equal to head. It starts from head, and while this temp is not equal to null, what do? I print the node. So I say s out temp dot data and take this temp to the next node. Temp equals to temp dot temp goes to the next node. This while loop will help me to iterate on the entire linked list, right? So temp starts from head, temp is referring to this node, I print out 30, temp equal to temp dot next. So temp dot next means this value. So this value means this node. So temp goes here. Again, temp dot next means this value. which is this node. Temp goes here. Again, this is not null. This node is not null. So I say temp dot next, which is this value, which is null. So temp actually becomes null and my loop stops, right? Now the display method is there and we can run this code. Okay, so I see 30, 20 and 10, which is okay. That means my linked list is getting created. But to show you in a linear fashion, what I can do, I can put an arrow here and I can put a new line here, right? This will make the representation look little better, right? I'm getting 30, 20, 10. Now, if you look carefully, I added 10 in the beginning, so 10 got added. That means my head and tail both were here, right? Then I added 20, in which 20 got added here, and my head moved here, right? Then 30 got added, a new node was created, it got connected here, and then my head moved here, right? This is how the linked list is going to look like 30, 20, and 10. So I hope you're able to understand the add first method, right? Now, on the similar lines, what we will do, we will implement the method called as add last. Now, take a pause and think how you will implement the add last method. All right, let us see, right? Now, suppose you already have a linked list A, B, C, right? And I want to add a new node D, which is at the end of the list. So this is my head and this is my tail, right? So how do I add a new node here? First of all, I need to create this new node. So how do I do it? I can say, okay, fine, node n, this is equal to new node, and I give the data to this node that I'm getting, right? Now, how do I connect this tail node with the new node? So that connection is pretty easy. What I need to do, I need to update this value and give it the reference of this node, which is stored in n, right? So I need to say that fine tail dot next, this is equal to the new node that we have created, right? So this makes the connection, and I also need to say, okay, this tail should be here because this node is now the new tail, right? So I can say tail equal to tail dot next, or you can say tail equal to n. Both are fine, right? Now this tail has also moved. And one more thing we will do is we will just size plus plus. Now this will work fine when the linked list is already there, right? But think of a case when your linked list is not created. That means both head and tail, they were null, and you inserted the first node by calling the add last function. You say, okay, I don't have a linked list. That means if the size is 0 and you're adding the first node in the linked list, then how should the update should happen, right? So you still created this new node n, right? With the data d, n is referring to this node. So in this case, both head and tail should get updated. They should point to this node, right? So what I can do, I can say, okay, head and tail, they will refer to n, right? They will also store the address that is stored in n, right? Now you might ask, okay, what happens to this n? So n is a local variable. It will get destroyed after this function call is over. But head and tail, they are the data members of the class. They will exist till you have the linked list object in your memory, right? So they are not going to get destroyed, right? So n is a local variable. It will be over, right? And anything that is allocated using new will not get destroyed. Why? Because if someone is referring to this memory, that memory will not be garbage collected, right? So head and tail, they are referring to this node. N is a local variable. It will get destroyed, right? So this way, add last will work. So now let us test our functionality, right? So I say, okay, l dot add last. Maybe this is 40 this time. And again, I say, okay, l dot add last. This is 50, right? Now, if you look carefully, I'm adding the first node by calling add last function. First 40 was added, add first 10. So 10 was added, then 20 was added, then 30 was added. Now again, I'm calling the add first method on a linked list which is already built. So 50 should get added, right? So if I say l dot display, right, it will give me this linked list. Let us see the output. So we are getting this linked list 30, 20, 10, 40, 50. That means this is working really fine, right? Okay, let us go back here and let us implement one more method. That is, okay, give me the size, right? How many nodes we have. So that's going to be easy. Public int get size, and what we are going to do, we are going to return the size of the linked list, right? Now we are doing it this way because if you make this size public, anyone can change it, right? So I'm only giving the getter to access the size. I'm not giving any method to set the size of the linked list. Okay, so that size should be updated only through the add and the remove methods. So this is also fine. So I can say l dot get size, and I want to display how many nodes I have in this linked list. This is again a order one operation, right? So I can say, okay, there are 5 nodes. Now let us talk a little bit about the complexity. So your constructor is doing order one work. At first, it is also doing order one work. No loops involved. Here also we are doing order one work. Get size, we are doing order one work. Display, we are iterating over all the n nodes. We are doing order of n work, right? Now the next method is add, right? So take a pause and think how you will implement add method, and if you want to insert something in the middle of a linked list at a particular index. Okay, so let us see it next. So we are discussing how do we implement the add method. Okay, so we are given, okay, this is the data that you need to add, and you have a particular index at which you want to do this insertion, right? Now suppose my data is 4 and my index is 3. That means, okay, 0th index, first index, second index, here I want to add, like at the third index the new node should come, right? Or you can say, okay, after 3 nodes I want to insert the fourth node. So this is my fourth node that I want to insert somewhere here, right? So how I will do it, right? So one way is, okay, I will create a new node, n is referring to this node 4, right? But how do I connect 3 with 4 and 4 with 5, right? So this is going to be easy. How? You can say, okay, let me create this new node n. So node n, this is equal to new node with my data 4, right? Now one way is, okay, I can say I need to reach this node, right? How do I reach this node, right? That means if I start from this node, right, and I want to reach the third node, right? After 3 nodes, I have to insert. That means I have to reach the third node. So if I take one jump here, I reach 2. If I take one more jump here, I will reach this node, right? That means in order to reach 3, I need to take 2 jumps, right? Okay, so if my index is some p, right, I need to take p minus 1 jumps, right? For a particular position p, I need to take p minus 1 jumps. This we will do it using a loop, right? Let's say I've reached this node and I'm holding this address in a variable called temp, right? Now how I will do it, right? So I can say, okay, temps next should point to 4. If I do this, temp dot next should refer to n. What loss I will have? I will lose the address of 5. I don't want to do that, right? How should I do it? I will say that before doing this operation, let me say that 4 should store the address of 5. Can I do that? Of course, yes. How do I do that? I can say n dot next, that is the next of 4, should refer to 5. So what is the address of 5? It is nothing but it is the next of temp. So it is temp dot next, right? Once it is done, can I update the address, the next of 3? Of course, yes. I can say, okay, 3 is next, now should point to 4, and this link will automatically get broken. So I can say 3 is my temp dot next should be equal to n. Right? So in just these 3 steps, I will be able to insert a node in the middle. Right? Now we might have a special case where we might need to insert a node in the beginning or at the end, or we are getting an index which is out of bounds. So let us see how we will handle those cases. So first of all, I'm going to check if this index is out of bounds, right? So if my index is less than 0 or my index is greater than the size of the linked list, that means I cannot insert this node, right? So in this case, what we can do is either we simply return, right? But that's not a good idea. We should tell the user that you are doing something wrong, right? So one way to do it is we can throw a new exception and we can say, okay, index out of bounds, right? That you're using the incorrect index. And here I have to say, okay, this method throws a exception, right? So I can throw an exception in this case, and an error will come in the main when this program is executed, right? And now if my index is 0, that becomes a special case. That means, okay, I'm trying to add something at the beginning, so that I have already handled. We can just call the add first method with data, right? So I can say, you call the add first and you give the data. That's it. Else if your index is equal to size, that means if the linked list has 3 nodes and you want to insert something at index 3, that means you're inserting something here, right? Which is again at the ending of the linked list. In that case, you can call the method add last and you can give the data, right? So in the else block, we have to write the exact logic that we are talking about, right? So let's see how we will do it. Suppose your linked list is like this: 1, 2, 3, right? And I have 5, 6, 7, right? So I'm telling you that, okay, after 3 nodes, you have to insert a data that is 4, right? So how do I do it? First, I need to reach the third node, right? So I need to take a temp and reach this node. So temp will start from head. So I can say node temp, this is equal to head. How many jumps I have to take? I have to take index minus 1 jumps. So I can say, okay, for int jump equal to 1, jump less than equal to index, right? Jump plus plus, right? Or if it is sounding confusing to you, you can say less than equal to index minus 1, right? These many jumps, as I told you, we have to take, right? Now in each jump, what we should do, temp will take a step. So temp will go to the next node. Temp equal to temp dot next. Now I'm in a good position to do some insertion here, right? What I will do, I'll say, okay, let me create a new node n whose data is 4. I can say node n, this is equal to new node with the given data, and n dot next should refer to temp dot next, as we have just discussed here as well, right? So 4 should get connected with 5. That is the first step. Then I need to connect 3 with 4, right? So how do I do it? So 3 is my temp dot next should point to 4. So 4 is n. That's it. And size plus plus. Size we will update here. So here we are not doing size plus plus because add first and add last will automatically increment the size, right? That's it. So that is my insertion in the middle. Now let us run this code in main and see if it works really well or not, right? Now I can say, okay, this was my original linked list. L dot add at index. Let's say I want to add at some index 0. Let's say the data is 0, right? L dot add at index. I want to add something at the last index. So L dot get size. Okay, now I'm getting not add last, but I can say add at. So index will be, let's say, the last index. So data is, let's say, 100. L dot get size. Now again, here I'm getting this because I've not written throws exception. So main can also throw an exception because it is calling a method that throws exception. So main can also throw exception, right? So we have to write this here, right? And let's add something in the middle as well. So L dot display, and I will say, okay, L dot add at index 4. Sorry, data is 4 at some index, let's say 3, right? Something like this. And again, let me say L dot display. So this will test our all the 3 cases, and we should be seeing that they should work fine, right? So in the first case, I added 0 in the beginning, fine. I added 100 at the end, fine, working fine. Then in this linked list, I said, okay, at index 3, I should insert 4. So 0, 30, 20. This is the third index. So before 10, I will insert a 4. So 0, 30, 20. I'm getting a 4 here. Then 10, 40, 50, and 100. That means in the middle, it is also working fine. And I display this list, right? And finally, I have 8 elements: 1, 2, 3, 4, 5, 6, 7, 8. That means that size update is also working fine in all the 3 cases, right? So that completes part 1. That means we are able to add nodes in the linked list in all the three cases. We have seen add first, we have seen add last, and we have seen add in the middle, right? Next, we will move on to get, and after that, we will move on to remove. Right? So take a pause and think how you can implement these methods: get first, get last, and get an element at a particular position. It's your time to code, and I'll just show you the add method, right? So pause this video here and try to implement these three methods. Let us implement the get method, right? So I need to write a method called public int get first. That means I want to get the first element of the linked list. But what if the size of the linked list is 0? I do not have any such element. So I will have a special case. If size is 0, I can throw a new exception that the linked list is empty, right? So linked list is empty. That is the error that I'm trying to show to the user, right? And here I have to tell that, okay, this method also can also throw exception, right? So throws exception. But if the size is not 0, the linked list is there, then it is pretty easy. We just need to return the data present in the head node, right? So head is referring to this node, access the data and return it. So return head dot data. That's it. Size will not change, and this is what you will do. So similar to this, you can also write get last. So again, if the linked list is having size 0, then there is no last element. You will throw an exception, and in that case, the last data will be at the tail node, right? You can say return tail dot data. That's it. Now, if you want to get something in the middle, that is going to take one more step, because you will have to loop through it, right? Okay, so add at we did not discuss. It's going to take order and time, because your the worst case you might have to loop till the second last or the last node, right? So get last we have done. Now this will be get at a particular index. If I give you an index and I want to get an element at that index, how it will work out. Take a pause and think how you will do it. This is also easy, right? Now user is giving you an index. Now it is possible that this index is also out of bounds, like we saw here, right? Like in the case of addition, it is also possible that this index is out of bounds. So if index is less than 0 or it is greater than size, I can throw an exception index out of bounds. Then if this is not the case, right? So if this is not the case, if the user is uh, really giving you a valid index, right? Else if it is possible you're talking about index 0. If that is the case, you can say return get first. This can happen. Else if index is equal to size, you can say return size or size minus 1. It will be size minus 1, because the last element will have an index size minus 1. You can say return get last, right? Otherwise, what you need to do, you need to iterate on the linked list, right? So that iteration part is easy. What we will do, we'll have, let's say, A, B, C, D, and so on, right? This is index 0, 1, 2, 3, 4, right? So I want to get something at the second index. What I need to do, I need to take one jump, one more jump, two jumps to reach this particular index, right? So that means take the number of jumps equal to that index. So I can say, okay, fine, node temp that is equal to head, and for int jump equal to 1, jump less than equal to index, jump plus plus. What do? I take my temp to the next node, temp equal to temp dot next. Once I reach this node, I need to return the data of that node. So return temp dot data. That's it. So I take my temp here and I return this data, right? This will give me the data at a given position. So that is my get at a particular index. Now let us test this code. So I want to say, okay, fine. In this linked list that we have, I want to get the 0th element, s out l dot get first, s out l dot get last, and s out l dot get at index 4. Let's go and run this code. The first element is 0, last element is 100, the fourth element is 10. Let us verify. So zeroth index, first index, second index, third index, fourth index. So fourth index is really 10. That means my output is correct. That is how we build the get art methods in the linked list. So far we have seen the add method and the get methods. Okay, all the three versions. So getting first, adding first, they all take order one time, but doing some work at a particular position, they take order of n time, right? So other methods are all one. Now we have the remove method. We want to remove first, remove last, and remove at a particular position. Let us see how we will write these methods. Okay. So what I will do, I'll create remove methods, public int. So remove, I will also get the data that has been removed from that particular index. So return type would be int. So remove first. You might think it should be very simple. Whatever is at the head, I will return that, right? So I want to remove this. Let's say 10 is there, 20 and 30, and this is my head. How do I remove this node? Right? So one way is, okay, you can store the output, that is going to be head dot data, and then you can say, okay, this head will move to the next node. So head will go here, right? So head is going to be at head dot next, right? So doing this, will it remove this node? The answer is yes. So in heap, this node is a node that no one is referring to. What will happen? It becomes eligible for garbage collection. The garbage collector will come and it's going to sweep away this memory. So that means now your linked list will be only this, right? But there are few special cases, right? So I can say the output will be returned. That's okay. You also need to reduce the size. This dot size minus minus. This is something we need to do, right? But what is the special case? If the linked list is empty, can you remove the first element? The answer is no. So we have to check if the size is 0. What we will do, we'll throw an exception. Right? We'll say throw new exception that linked list is empty. Right? Fine. And we need to tell that this method throws exception. Now, what about if the size is 1? Right? So head will get updated fine. But if you have just one node and both head and tail, they were pointing to this node, will it form a special case? Of course, yes. Right? If this node is getting removed, what will happen to head and tail? They will be reset to null, right? If your original size was 1, how do you remove it? You will set your head and tail equal to null. Size will become 0, right? Okay. And else, sorry. Yeah. So one thing we can do is this code, we can move here. Output is equal to head dot data. Okay, and we'll of course return output. This code we can move in else case, right? That means if there are like at least two nodes, in that case tail will not be affected, right? So what about this case, else case? If there is 10, there is 20, and there is 30. So this is my head, this is my tail. Even if my remove this node, head comes here, right? So head goes to the next place, size gets reduced, so tail is not affected, right? But if I have just one node and I remove that node, in that case, head and tail both will be affected, so they are reset to null and the size becomes 0. So that is how the remove first method should work. Now let us test this method. Let me create a new linked list. Let's say I add at the first position, let's say 10, then I add 20, 30, 40. 20, 30, 40, and I can say L dot display. Then I can say L dot remove first and L dot display, right? So I'm getting 40, 30, 20, 10, fine. And if I remove the first element 40, my linked list is 30, 20, 10, which is fine. Okay, if I have just one element in the linked list, and let me see if it works well. So I have one element, I remove that one element, so my linked list is empty. Fine. That also works well, right? And I can say s out L dot size. I want to see if my size is getting updated properly. Yes, the size is 0 and I don't see any output here. That is how I will implement remove first method. Now on the similar lines, can you implement the remove last method? Okay, just need to think what will change, what will happen to head and tail, how much time it will take. So this method, it's going to take order one time, right? Remove first, but you have to think how much time remove last will take. Okay, so let's see remove last. Okay, so first case is, okay, if your linked list is empty, you cannot throw anything, you cannot remove anything. So if your size is 0, you will throw a new exception. Okay, then similar to this one, your output in this case will be what? Your output will be now tail dot data. You know the last node is tail and that data is your output, right? So if your size is 1, what you will do? You will reset your head and tail to null and you will say size is 0. If this is only one node, both head and tail are referring to this node. You want to get this data, you store this data in a variable called output, that is tail dot data. Original size was 1. If this is removed, head and tail, they are reset to null and size becomes 0, which is correct, right? Otherwise, if you really want to remove something, right, so you will have to check that if your index is in the bounds, or is it 0, or is it the last index. Sorry, you don't need to check here because we are talking about remove last, right? So you just need to remove the last node, right? So what I will do, I'll say, okay, else we have the other case, we know what node to remove if there are more nodes, right? There is one tricky thing here, that if it is a single linked list, right, and this is your tail node, you're saying I want to remove this node, right? That means tail should be updated, tail should come here, the new tail should come here, right, after removing this node. So I've stored this d in a variable called output. So output is tail dot data. So output is d, right? But how do I bring it back? There is no way to do it, right? Even if you maintain, okay, I'll maintain previous of tail for every node. Suppose this was the previous, but when you remove C, how you will get the previous? So the answer is we don't have any order one way of coming to the previous node. We have to iterate from the beginning to reach this node, right? So that I can update my tail variable, right? So this is going to take time, right? Or the other option is you maintain a doubly linked list in which every node is also connected back, right? If you do that, your remove last will work in order one time. But for now, we have a singly linked list. That means we have only the next address, right? Singly linked list. In that case, we have only one option, start from the head node and try to reach the second last node. So how do I do it? So I take a variable called temp, which starts from head. I can say while temp dot next is not equal to tail, right? So what is the stopping condition? When I reach this node temp dot next, this is equal to tail, right? So this is the tail node, right? Suppose this is my C, this is my temp, and this is my tail node. This is my D, right? I'm saying while temp dot next is not equal to tail, right? Until this condition is not met, I will take my temp to the next and next node. So temp starts from here, it goes here, it stops here, right? Because C's next is equal to tail. So temp will stop at C. So I can say temp equals to temp dot next. My temp stops at the second last node, right? Now why this is important? Because I want to update the tail thing, right? Now at this point, I want to disconnect D. This D I don't want. So what should I do? I would say temp dot next is equal to null. So if I reset this variable to null, what will happen? This object becomes eligible for garbage collection because no one is referring to this object, right? So garbage collector will come and sweep away the memory of D because there are no object references which are holding the address of this node. So this D will get deleted from the memory and C's next is updated correctly, right? But what about the data that we wanted to return? That is still copied in a variable called as output, right? So once this is done, what should I do? So temps next is now null. This tail should be updated. So this tail should come here. So this tail will become equal to temp and the size will also get reduced, right? So here we have reset the size. So here it will be one lesser, size minus minus. That's it. And I will return the output in both the scenarios, right? So return output. In this case also I'll return the output. In this case I will also return the output. That is how remove last will work. And if I now show you L dot remove last, and maybe if you want to output, that's okay. We just want to see the linked list. So I can say L dot display. What do I get? Okay, let me add some numbers. Only then we can see 20, 30, 40. So right now I'm getting an exception because it's an empty linked list. So 10, 20, 30, 40 L dot display, and then I called the remove last method. So this was the linked list. I removed the last element. This is what I am getting, and the size is 3, right? Which is fine. That means the remove last is working as expected, right? Now the next thing we would like to do is, any guesses? Of course, it's going to be remove at a particular index. So we want to write one more method, public int remove at given index. So again, before I write the code, take a pause and think how you will implement this method. Given a particular index, I want to remove something from that index. Let us start implementing a remove at, right? So first thing is, if the size is 0, that means you cannot remove anything. So you will throw a new exception. So throw exception, throw new exception, and you will say, okay, linked list is empty. You cannot remove it. Or you can check that if the index that you're getting is out of bounds. So if index is less than 0, or your index is greater than size, you cannot remove, or equal to size. Even at size we don't have anything. The last index is size minus 1. So if this is the case, I have to throw new exception, right? I'll throw a new exception, and we'll tell that this method can throw an exception. All right, so the error is fixed. Now what to do? I still want to remove it. So if my index is 0, that means I want to remove something from the head that we have already implemented. So whatever is returned by the remove first, we will return that. Else if index is equal to the last, which is size minus 1, we'll return whatever is removed by remove last method. And now is the time we will see the actual working of this method, right? How do I remove something from the middle of the linked list? So let's say I have a linked list like this: A, B, C, D, E, F, right? And I say, okay, I want to remove something from index 2, right? 0, 1, 2. I want to remove this element. So if I want to remove this element, that means B should get connected with D, right? And this link from B to C, it should get broken, and C should be garbage collected, right? If this happens, C will be deleted from the memory, right? So how we are going to achieve this, right? So first of all, we need to reach this node, that is B, right? So if my index is 2, I need to reach one node behind that index. So how do we reach that node? Again, fairly easy. I can say I will start with temp, that is equal to head. And if index is 2, that means I need to iterate one less than that index. For int jump equal to 1, jump less than index, jump plus plus. So if it is 2, I'll just take less than 2 jumps. That is, I'll take one jump. I will come here, and at this node, I will start doing certain operations, right? So first of all, let me take temp to that particular node. Right? Now I'm standing at this node. So what I want to do, I want to return this node, right? I want to return the data of this node. I will copy it in a variable called output. Output is nothing but temp dot next dot data. That is what my output is, right? And I want to return that output. Or let's say this is my node, which is okay. Either way we can do it, right? Node called output. So this node is my output node. And what I want temp to connect with next of this node. So I want B to connect with T. So how we can do it? So temp.next, either you write it should be equal to temp.next, which is my output dot next. So that is my D. Or you can say output.next. Again, I'm connecting B with D, right? Now no one is pointing to C. It will become, it will get garbage collected, right? Okay. And if this node is garbage collected, this link is automatically broken. So what I need to do, I need to say size minus minus, and I need to return output dot data. Output dot data. This output is a local variable, right? It is there only in this function. Once I return output dot data, there is this function call is over. Output will be out of scope. It will get destroyed, and hence no one is referring to C. This memory will also be cleared off. That's it. That's what you need to do, right? So that is going to remove something from the middle of the linked list, right? Now I can test my code. So I can say L dot remove at index, let's say 1. So given this linked list, let's say remove at index 2, which is okay. Show me what will happen if you remove something from index 2. So this is my linked list. And if I say, okay, remove index 2, 0, 1, 2, 20 is gone, I get 40, 30, and 10. That means the code is working absolutely fine. So this is how we can remove something from the middle of linked list. So far, we have seen the implementation of single linked list, right? So in which we said every node is going to store the address of the next node, right? But what happens in real scenarios, you might need sometimes a doubly linked list. So what is a doubly linked list? So just like you were storing the next, you will also store the address of the previous node. That means each node is now holding three things: a data, a next reference, and a previous reference. So 2 will hold the address of 3, 2 will also hold the address of 1, right? Now, the advantage of doubly linked list is that you can traverse in both directions, right? For example, we were doing removal at tail, in which I said, okay, I want to remove this node and I want this tail to come back. So if it is a single linked list, I have to iterate from the front to reach this node, which is going to take order of n time, right? But if I do it the same operation, deletion at end, for a doubly linked list, I can just come back to the previous node, okay? Because 4 knows the address of 3. So I can update my tail pointer very easily, right? So it comes at the cost of extra memory, but it can save some time. For example, if you want to delete something at the end, it can then be done in order one time. Insert at end can be done in order one time. Insert at head can be done in order one time. Remove at head can also be done in order one time. So at both ends, you can do insertion and deletion in order one time, right? So each object stores data and memory location of next as well as the previous object, right? So this is something you can implement, right? Now there won't be a lot of change. For example, if you're making a method to insert something in the middle, let's say I want to insert 5 here. What are the variables that you will have to update, right? So you will have to update that 2's next should point to 5. Okay, but if you do this first, what will happen? You will lose the address of 3. So what I will do is, I'll say, okay, let me create this new node 5, and let's say this is my temp. Here I want to insert it. So 5's next will point to 2's next. 5 gets connected with 3, right? I can also say 5's previous can point to temp. So 5 also connected with 2, right? Now I just need to change these variables. So I can say t's next will point to n. 2's 2 points to 3, right? And I also need to say 3's previous, right? Or we can do it other way, right? We can first say that this node, which is the next of 2, so t dot next, right? Dot previous. 3's previous should point to n. So this link will get like this. This link is gone. Now what you can do, you can remove 2's next and make it point to n. So you can say this will get connected here. So you can say t dot next, this is equal to n, right? So again, you just need to think logically and you need to execute these instructions in a particular order so that your updates are correct. You're not making any changes which are inconsistent, right? So again, all the operations get remove, add. You can try creating those operations on a doubly linked list as an exercise, right? So let's talk about what happens in Java, right? So if you want to use this class inside your collections framework, then this class is already implemented. So there is a class called as linked lists. So it's part of java.util package as a part of collections framework. By default, this class internally uses a doubly linked list, right? So if you're using this class directly in solving problems, you're getting a doubly linked list by default, right? So if you want to learn more about this, I have covered collections in my DSA tutorial on the channel. You can watch that and learn how do we use the inbuilt doubly linked list or inbuilt linked list class. You can definitely learn about the methods of that as well, right? So let us quickly revisit the features of linked list, right? So it provides us an ability to use the non-continuous memory locations, right? So if you have like different chunks of memory available in different parts of the heap, and you cannot create a big array, but what you can do is you can use some memory here, some memory here, some memory here, and you can just connect those chunks, right? Non-continuous memory parts can be utilized efficiently using a linked list. Second advantage is it's a dynamic data structure. There is no need to allocate pre-memory, and again this results in efficient utilization of memory. For example, if an array you say, okay, I need 1,000 elements, but only suppose 100 get used up, then what is happening? All this memory is it's a waste of memory. It's not efficient utilization of memory. So linked list, you create memory on demand, and hence you only use that much memory that is required, right? Okay. And if you are using a doubly linked list, insertion and deletion at the ends of the linked list, they are performed in constant time. So if you compare it with an array, and if you have to do some insertion or deletion in the beginning, right, you will know that it's going to take order of n time, because I have to do shifting. If I insert something or if I delete something, again I have to shift all the elements, right? And joining two linked lists is much more efficient in terms of space and time. So if there is one linked list and there is another linked list, right? So think, if you have to join two arrays, you have to copy all the elements from one array into another array. But if you have to join two linked lists, you just need to connect the tail of one with the head of other linked list, and that is going to be again an order one operation. So it saves both your space and time, right? So that is all about linked list. So a quick revision on the operations. Random access, if it is a linked list, it's a bad thing, right? Because it's going to take order of n time. In an array, getting the ith element will take order one time. Insertion and deletion at the beginning, order one time. In an array, it's going to take order n time, as I just discussed. Insertion and deletion at the end, right? So this, if it is a doubly linked list, it can be done in order one time, right? In an array also it can be done in order one time. Insertion and deletion from a random location. So if you're doing somewhere in the middle, both are going to take order n time, right? So in an array, this part is bad. Insertion and deletion at the beginning. Random access is good. In a linked list, this insertion deletion part is good, but random access is bad. So you can see each data structure has its own pros and cons. So depending upon the problem, you have to decide whether you will go with a linked list or an array.
In this video, we're going to have a 4 to 5 hours extensive course on linked list. We'll talk from the very starting what is the linked list, what is the need of the linked list. Also, we have discussed various aspects of operations on linked list like insertion, deletion. Along with that, we have solved a lot of problems. We have discussed doubly linked list. We have discussed linked list STL. We've also discussed circular linked list at some point. Along with that, we have solved a lot of problems ranging from lead code to interview bit, and the uh, topics have been very extensive. So if you're looking forward to prepare for linked list well, make sure you watch this entire tutorial from the beginning till the end. Also, do let me know if you have any queries, any problems throughout this particular lecture. You can comment them down in the comment section. I'll be more than happy to take from there. I hope you people enjoyed watching this amazing video. Also, don't forget to press the subscribe button and like this video. We have a lot of videos coming up on Scalar's channel, be it from system design to data structure algorithms to cloud technologies and a lot more. Make sure you stay tuned and subscribe this channel. All the best. Good luck. This video we're going to discuss about linked list, introduction of linked list, insertion in a linked list, deletion in a linked list, different operations that we can perform on linked list. We'll also try to see some important algorithms, some important concepts behind linked list, how we can solve different questions on linked list on different platforms. This is going to be an extensive 4 to 5 hours long course on linked list and will take you from scratch to advanced level in linked list. right? So we'll start from the very basic definition of things like storing, right? How we store data in programming, right? If let's say I want to store a variable, so we generally store a variable in this particular format like int a is equal to 5. So this is the format in which we store a variable in our programming, like while we are coding. Right now, let's say if I want to store a group of numbers together, let's say I want to store the roll numbers of top 10 students of your class. So, for storing them, either I'll need to create 10 variables. So, that will be a little tedious task. So, instead of creating these 10 variables, what I will do is we already know a data structure for this, that is an array. So, what is an array? Array is a basic data structure. It goes something like this. Let's say this is array. How we initialize an array, like this int specifies that the data that we'll be putting up in our array is of integer format, right? So this is the initialization of an array, basic initialization of an array, int arr, and in the brackets we are putting 5. So 5 suggests the size of this array. Let's say this is the array that we are putting in numbers like 1 2 3 4 5 6 7 8 and 9, right? So let me index this array 0 1 2 3 4 5 6 7 and 8. So indexing of array starts from 0, right? So this is how we store elements in a contiguous fashion. So in array gives us a privilege of storing elements in a contiguous fashion, right? So what if I say now I want to add two more elements in my array? So is there a possibility, and how array is like, let's say this, how we store this particular array? We generally store the address of the first element. Let's say this address is 100, right? And an integer takes 4 bytes. So this is 100, this will be 104, this will be 108, this will be 1112, this will be 116, this will be 120, this will be 124, 128, this will be 128, this will be 132 and 136. So the next number if I want to add should be at 136th place. But I'm not sure whether this 136th place is available for me or not, right? If I want to add another number after 9 in this particular array, so I am not able to add that number, right? So what, like, so this is a big problem. How we can solve this particular problem? So here comes the concept of what we are discussing is linked list. So how is linked list different from an array, and what actually is there in a linked list is, let's say, so now instead of saving elements in a contiguous fashion as we have seen above, what I'm going to do in this case is I'm going to, let's say I want to store four numbers 1 2 3 and 4, right? So I make a block and I take a particular memory block and I put 1 in that. I take another memory block and I put 2 in that. I take another memory block and I put 3 in that. I take another memory block, I put 4 in that. So I have four different memory blocks in my array, each having its own address. Let's say it is address 1, this is address 2, this is address 3, this is address 4, right? So there are multiple addresses that we can see in our linked list. So this is address 1, address 2, address 3 and address 4. So now, like, if I want to add a new element, I can simply create a new element, let's say 5, add address 5. So for this kind of a structure, for this kind of a data structure, what I actually need, I need to store these addresses somewhere, right? So maybe I can maintain something in which I'll be storing all their addresses, right? This is possible, right? But this will again be very tedious, right? Carrying, maintaining and storing addresses of elements somewhere. So this is again a tedious task. So I want to make it a little more simple. How can we do that? So is there a possibility in which I don't need to store all these addresses? So instead, like, there is a possibility. How we can do that is basically by connecting these elements. How we can connect these elements? Let's say I have one here, it is present at 100th location. I have 2 here, it is present at 200th location. I have 3 here, it is present at 330 location. I have 4 here, present at 450 location, right? So I want like these should be interconnected. I don't need to, I don't want that I should store their addresses somewhere. It will take me more memory, it will take me more operations. That is something that is not very required, right? So is there a way in which I can avoid that? So for avoiding that, basically I'll be creating something in which I'll connect uh, this element or this block with another block, this block with another block, this block with another block, right? And I will save the address of this block. This only saving this the address of this block will serve the purpose. So what can be done in this case is like I want to connect all of these together. So for connecting all of these together, there is a way out, right? How that will work? Let's say this is one, this is two. So we'll create a structure in such a way that this memory block is divided into two partitions. This first partition will contain my data of the node that I have, data that I want to store, right? And the second part will store the address of the next number that I want to store. So the address of next number is 200, so I'll store 200 here. Here it's 100. So the next node here is 330. I'll store the address of 330 here. Next node is 3. I'll store the address of next node, that is 450 here. This is 4. And now there's no node, so I'll store null here. Right? So in this way, what we are actually doing is we are connecting this 200. Now this 200 address is written here. That means I have the location of the next node. So both of these are connected now. This is also connected now. This is also connected now. Now I just need to store this address. Now if I have this address, this is the address 100. With this address, I can access any of the elements of this linked list, right? I don't need to separately store these addresses anymore, right? I don't need to separately store these addresses anymore. I can just store the address of the first element and that's it, right? So how will be like if like now you have seen this is a new kind of a structure, right? So when I say a new kind of a structure, it's something of this particular sort in which I am storing data in this part and I am storing the address of next node here, right? Data here and address of next node here. So is there any data type, like we already know data types like integer or character or float or double? So is there any data type that can store any this type of a structure in which I want to have an integer number here and I want to have a pointer number here, because address is generally stored in pointers? No, so there's no inbuilt data type of such sort. So instead of that, I will be creating my own data type. So creating my own data type means I will be creating my own class. So this whole structure, this structure that contains data as well as address of the next node, next we call this as node. This is known as a node. So we'll create this class node, and inside this class node we will have two data members. This is like first thing that we want to store is data, second thing that we want to store is address. So the data here is integer data, and what we are going to do is we are going to store the next address. So if we are storing address of something, so what we generally use in storing address, we use the pointer, right? But what will come here of pointer is of what type? Let's say if you have something known as integer a is equal to 5, how we store the address of this integer? We generally store it by ampersand a. Let's say I'm doing int star ptr, right? This is the way in which we store the address of a, right? So this is the variable like of what type, like I am storing the address of integer type, so I have this integer in the front. So here I am storing the address of what? I'm storing the address of the next node. So this complete node right? So what will be the data type here? It will be node star next. So this is the basic structure of class that we will be using ahead. This is how my first linked list will be. One node of the linked list will be made. Basic structure, basic understanding, right? Now, if someone says you to create a node, like this is the class that we have made, right? And once we are making a class, we need to initialize these as well. So to initialize these as well, what we do is there is something known as a constructor. As you people already might be aware, you all have studied object oriented programming, right? So constructor is required. So what will constructor do? Class node. Inside this we have int data and node star next. What else we need to do is we need to create a constructor. So constructor will be something like this. It will have an argument int data, and inside this what we'll do is we'll initialize this data and this next. So how will initialize this? We can use this this data is equal to data. What is this keyword? This keyword is the keyword that stores the address of my current object. Stores the address of current object, right? This ke data mein I am putting this data that is I am receiving in the argument. So this data is initialized. What I'll put in the next, I'll put null initially. So this is basically how a node is created. Initially, if a node is created, let's say I'm creating a node n1. So I need to pass on the data, let's say 1. So once I write this statement in my main function, what will actually happen? A node will be created. It will have two parts. The data part, one I am passing, one will be passed here, and the next variable will be initialized to null. So writing node n1 will create a new node with data 1 and next pointer as null. Right? I hope this is true. Right? So now let's just try to code in what we have written till now so that you can have a better understanding. Right? So we are here on the interview bit IDE. So the first thing that we were doing is we were creating a class node. Inside this class node, what happens is like we generally have access specifiers, be it private, public, and protected. So let's create a public data members. Int data. Second thing is node star next. Now you very well know why we are using this node star next. Next thing that we want is we want to create a constructor node int data, and I will be initializing this now. So how we are initializing this data, I was putting as data, right? And next is initialized to null. So this is what we have created, this node class. How we'll create our nodes? Let's say I want to create my first node. So how will create my first node? Node n1, and in the bracket I'll put 1. So what does this statement means? This statement here, node n1 bracket 1, means that I have created a new node with data 1 and next pointer is initialized to null, right? Let me create a node n2 with the data 2, right? I have created two nodes, node n1 with data 1 and node n2 with data 2, right? Now I want to connect these two nodes. How I will be able to connect two nodes? Let's just try and see. Right, so what happened like this is we have written node n1 1 and node n2 2. So these are the two statements that we have written, right? So this statement refers that I have created a new node with the data 1 and next pointer as null. This statement means I have created a new node with the data 2 and next pointer as null. Right, now I want to connect these two nodes, right? I want to have a structure of this particular format in which 1 is connected to 2. How I can do that? I can do that by connecting, like this will have a certain address, right? Let's say this address is 100, the address of this is 200. So if I put 200 instead of null here, so now my first node is storing the address of the second node and second node is storing null. That means my linked list is connected now, right? So what we need to do is we need to put n1 dot next is equal to and percent of n2. And percent of n2 suggests address of node 2, and we are putting the address of node 2 in my node 1's next, right? I hope this is clear. So I just want to do this, and let's just try to print after that how it goes, right? So I have node 1 and node 2. What I did there was n1 dot next is equal to and percent n2, right? And now let's just print cout n1 dot data, n2 dot data, right? So this is what we have done till now. Class ends with a semicolon, and now try to run this. So yeah, we have successfully executed the code. We have two nodes coming ahead, that is 1 and 2, right? I hope this is clear to you. Great. So now we'll try to see something else, like we'll try to create more number of nodes, and so that you can have a better clarity. So now that we have talked about, we have seen how we can output, we can print n1 dot data and n2 dot data, right? So now I want a thing in such a way that I don't need to know both the nodes of this linked list. I just have one pointer through which I can access the entire linked list. So now currently my linked list looks something like this. It's n1, it's n2, here it's data, here it's address of n2, here data of n2, here it is null, right? So in this way, this is the format of how a linked list would look like, right? So now, what if I store the address of this particular node in a variable known as head? So this variable, this starting node of my linked list is known as a head variable, and I'll use this head to access the entire linked list. So this head can be like head. What will this heads next represents? Heads next represents the second node. What will be heads next? So what will be this? This will be the third node, and so on. In this way, we can access the entire linked list using the head. Let me just show you in the IDE that how we'll be doing this. Right. So now we have created node n1. Let me create something as node star head that is equal to address of n1. Now I'll be printing the data using this only, right? How we'll do that? We'll do heads data and head के next का data. Let me just try and print if it is working all right. Yeah, so we are getting 1 and 2 again just by the first node of the linked list, right? So now we have discussed this. Let me take you to some point where we create multiple nodes and we try to print all these nodes in a linked list. So how will we be doing that? So let me just I just want to let you know what I'm actually trying to say, right? Let's say there are multiple nodes, that there is n1, there is n2, there is n3, n4, n5, and I want to print all these nodes. How I'll be printing? And I have just this head of the linked list, right? This, let's say we have this particular linked list, and this is null. Address of 1 is 100, and 100 is stored in my head pointer, right? So now using this head, I want to print this entire linked list. So what will be the steps that we can follow? There can be multiple steps, there can be multiple ways. So if I want to print this particular linked list, so the first thing that I will be printing is 1. So how we can print 1? We can do cout heads data, right? Cout heads data. After we have done cout heads data, the next thing after this is what we'll do. We'll move head equals to heads next. So what we are doing in this particular line is, like, initially the value of head is 100, right? Now we have moved the value of head to heads next, right? So the value of 100 changes to 200. That is the address of 2. Let's say it is 300, it is 400, it is 500. Now we have done this, we have used this particular line. Now we are at second node, right? Now again, if we print heads data, here the output was 1. Now again, if we print heads data, the output will be 2 in this case, right? Again, what I'll do, head is equal to heads next, right? So this 200 will change to 300. Again, if I'll print heads data, it will give me 3. So in this way, we can print the entire linked list, right? So let me create these 5 nodes, connect them together, and we'll try to print it using a print linked list function, right? You will understand it a little more better when we'll code it on screen, right? So what I'm trying to say is, like, we have already created node n1, we have created node n2. Let's create node n3 as well. Node n3 with data 3, let's say. Node n4 with data 4. Node n5 with data 5. Right now, what I want to do is, I want to connect these nodes together. So connecting these nodes together means n1 के next में what I'll put, address of n2, right? This is something that we're written again. Similarly, we'll do it for other nodes as well. Sorry, right? So here it will be n2's next will have address of n3, n3's next will have address of n4, n4's next will have address of n5, and we are done. Now we have head variable, head pointer, that is storing the address of my first node. So I'll simply call upon a print linked list function, that, and I'll pass head in that function, right? Now I need to create this print linked list function. Let me just remove these 2 lines of code as well. So yeah, let us create this void print linked list, and I'll be passing node star root. Let's say this is the head that we are passing on, right? Let me just call it as head only, right? So after this, what I'm going to do is, the first thing going here, what we'll do is, I'll put a while loop. I'll say while my head is not equal to null. So the first thing I'll do is, I'll see out heads data, right? And I will do head is equal to head arrow next. So what does this line represent? See out heads data. So firstly, we have passed head, that is, we have passed this first node. So it will check if head is equal to null. No, it is not equal to null. It will move inside, it will print heads data, that is 1 will be printed. It will change head is equal to head arrow next. This is what we have seen here. Head is equal to head arrow next every time we are doing, and the address of the next is stored in the head. Now again, second time 2 will be printed, then again head is equal to head arrow next, 3 will be printed, 4 will be printed, and 5 will be printed, and we'll finally have the printed linked list. Let me just try and see if we can print the linked list using this. So yeah, you can see that we have successfully printed 1, 2, 3, 4, and 5. So this is that the function is working, right? Let me just do one thing. Let me just copy this function and paste it here. So what do you think will happen? Just pause the video and think. Yeah, I hope you have thought on what will happen. So now, as we are changing head every time, we are changing head, we are printing the data of the head, and we are changing head is equal to head arrow next. So once we are out of this loop, our head is pointing to null. So now if head is pointing to null, this will not go inside this loop and will not see any difference in the output. So it our linked list will not be printed twice, but once. Why? Because our head will be null at this point. So, but this is really wrong, right? We need to use this head. We might need to use this head multiple times throughout our function. So instead of using our head directly here, let me just pull it down. So instead of using our head directly here, what I'll do is I'll create a temporary node. Node temp is equal to head, and I'll perform all operations on this temp. While temp is not equal to null, cout temp's data, and temp is equal to temp arrow next. So this is what we need to do, and I hope this will also be printed. So in this way we have successfully printed our linked list, and I hope you are clear with the basics of linked list. Now we'll move on to some other concepts of linked list, right? So now we have seen how we use linked list, how we print a particular linked list. Now let's move on to some operations that involve linked list, right? So if we are to do some operations, let's say insertion to begin with, if we are to insert something, let me just, yeah. So for insertion in a linked list, so what is going to happen? Let's say you might know the case of an array, right? If we are given an array of such a form in which there are certain numbers like 1, 2, 3, 4, 5, 6, and so on, right? And like these are the indexes 0, 1, 2, 3, 4, 5. If let's say I want that you should insert a certain number 70 at index 2, so what you will do in case of an array? So we very well know that in case of an array, I'll have to make this space vacant so that I can add 70 here. So for that case, we need to move all these elements that are after second index. We need to move them one place back. So that involves transferring this to this, this to this, this to this, this to this, and this space becomes empty. We'll add 70 here, and we have inserted an element. This is something that is considered to be a negative point in case of arrays. So if we are talking about linked lists, right? So we have seen what are the advantages of linked list. So how will this process of insertion go like in a linked list? So linked list is something like 1, 2, 3, 4, 5, and null. So let's say we have this linked list and I want to insert same thing, want to insert 70 at index 2. So let's just name the indexes. This is 0, 1, 2, 3, 4, and so on. So this is the second index. We want 70 to be inserted here. So for that matter, and like generally for a linked list, what we are given this head that points to the address of this first location, and we want to insert 70 at the second index of the linked list, right? So this is to be done. So what we can do in this case is, let's say we will be shifting the pointer, the next of this first node, like the node that is just before this index, to the address of my new node, and the next pointer of the new node to the next pointer of my previous node. So this is the very general overview. We will go in depth of how this everything is happening. Let me just take you to a new page, right? So yeah, so we want to insert, now we want to insert a new node in linked list. Let's say we are given an example. Let's write it very neatly. 1, 2, 3, 4, 5, and null. What we are given is head. Let's say the head initially is, like the address of this is, let's say it's 100. So let's say the head value is 100. What we are given is, we are given a certain data that we want to add. Let's say we want to add 70. We are given a position, that is ith position, that is the second position. We want to add 70 at the second position, that is, if we index them, let's say if I index it as 0, 1, 2, 3, 4, right? So I want to insert data 70 at second index, that is my linked list after insertion should look something like this. It should look like 1 2 70 3 4 5 and null. This is what I want. This is my final output. So how can this happen? Okay, so we have already discussed like what happens in a linked list. Basically a linked list node is of this form, right? A node has something known as data and something known as next pointer that stores the address of the next index. Now this node, let's say 1 will be having the address of 2, 2 will be having the address of 3, 3 will be having the address of 4, 4 will be having the address of 5. Let's consider these two nodes, right? Let's consider node 2. Let's consider node 3, right? Let if this address is 100, let's say we consider its address as 200, it says 300, 400 and 500. So 1 will be having the address of 2, that is 200, 2 will be having the address of 3, that is 300, will be lying here, 3 will be having the address of 4, that is 400, will be lying here. Now what I have been told is I have been told to add a node 70 here. So to add a node 70 here, first thing is from this head I need to move to this place, a place one less than my index value, right? So I need to reach this place. First of all, the first task is to reach this place. This is one thing. What will I do after reaching this place? I have been given this data. I have to create a new node with this data, right? So if I was to create a new node with this data, so how the new node looks like? New node is something like this is my new node. Data is 70 and address we don't know, so it is null. So I've created my new node and I want to insert this new node in between both of these nodes, right? So till now, what things we know? We know one thing, that is we need to create a new node with data, right? Second thing is we want to travel till the one index less than my given position. Travel till one index less than the given position. So how will start writing the code, right? Let me just take you to the IDE so that you can get some better insights. Okay, so this is our IDE. What we have done till now is we have created a node, we have printed that node, printed a linked list, and we have a certain linked list. Like this linked list is currently having these nodes 1 2 3 4 and 5. So this is the current linked list that we have right now, right? So what I need to do is I need to create a new function or so that I can insert a new node. Let me just create a new function by the name of insert node. So what this insert node function will be having? So the first thing that so as to perform anything on any linked list, we need to have the head pointer of that linked list. So one head will be passed. Second thing that is passed is int data. What is the new, like what is the data that we are going to add as a new node? Third thing is int I. So I stands for at which position I want to add the data. Let's say I want to add 70 at the second position. So if I want to add 70 at the second position, my data value will be 70, I value will be 2. This is what we have passed as our arguments, right? Okay, so let's see how we'll start with the things. We just know some part of the thing that we are going to do, right? So first thing that we are going to do is we are going to create a new node. So how to create a new node? Let me just name it as node star new node, and in what are the parameters? That new node, and inside this node I'll put in my data. So this line creates a new node. This line creates a new node of this particular format. Data is here and this is null. So this is what we have done by writing this particular line, right? Next thing is we know we don't prefer writing head. Instead we use temporary function, temporary node that will work as our head. So let me just start with the node temp is equal to head rather than doing anything, any operation with our original head, we try to maintain a temporary variable, temporary node that points to my head and will do all the operations on this head, right? So now, first, after creating this, I need to reach to a point. I need to reach to a point. I have this linked list 1, 2, 3, 4, 5, and null. So I want to reach to this point if I want to insert my number at the second index. So yeah, for this reaching, what we'll do? So we'll use a while loop. While let me just maintain a variable count, which value is initially 0, while the value of count is less than I minus 1. I minus 1 suggests that a position that is less than the actual index, right? Because we want to go to one node previous to that index, right? So what we'll do inside this loop is we'll do temp is equal to temp arrow next, that is we are going to the next node every time, and we are increasing the value of count, that is count plus plus. So what this function is doing, right? So let's just take this example as only. Okay, so what we have done till now, so we have been passed a linked list, like this is the head of the linked list, this point, the head points to this, its address is 100, its address is 200, 300, 400, 500. The value of initial head is 100. What we do, we create a new node by the name of data. I have created a new node. Let's say its address is 800. Data that we have passed is, let's say, 70, and this is initially null. This line is done. Now we have created a new node, that is temp, that points to my head. So instead of this, I have created a new node temp. Its value was also equal to 100. I have made a new variable count. Its value is equal to 0 initially. I'm checking this condition, and the value of I that we have passed is 2 here. If count is less than 2 minus 1, is count less than 2 minus 1? Yes, it is 0. It is less than 2 minus 1. We'll go inside and we'll make temp is equal to temp arrow next. Temp is equal to temp arrow next. So 100 will be changed to 200 and value of count will increase to 1. Now again we'll move into the while loop. 1 is 1 less than 2 minus 1? Is 1 less than 2 minus 1? So what is there anything that we are doing wrong? Let's just see, right? So now we have temp is equal to head, while count is equal, the initial value of count is 0. Now we have increased value of count to 1. Now if we move on to this while loop again, so what will happen, the value of count is now 1, I minus 1. So what is the value of I was 2. 2 minus 1, that is 1. So we'll not go inside this loop, we are simply here only. So do we need to add this on this location? Are we planning to add our new node at this position? No, right? We want to add at this particular position. So we will be using count is less than or equal to I minus 1. Let me just type in here. There is something that we are missing, right? So while count is less than or equal to I minus 1, we are doing the same things, and we have reached till here. Like if the value of count is less than or equal to I minus 1, so now count value is 1. Again 1 is less than or equal to 2 minus 1, that is 1. So we'll move inside the loop, we'll increase the value of temp to 300, but increasing the value of temp to 300 will make it here, right? And that we don't want, we just need its value till here 200 only. Why? Because if we have the value of temp 200, then we can simply put in the new node at this position and this node at this position. So we don't need to go inside the loop, we just need to have 200 in its place. So we will not do this equal to sign, right? This is actually wrong. So it will be count less than I minus 1. Let me just explain it to you once again in that page so that you can get a better clarity what we have done, right? let's just yeah. So yeah, this is what we were doing. We've had this linked list 1, 2, 3, 4, 5 and null. We have head that is pointing to 100. This is 100. This is 200, 300, 400, 500. We want to add a new node with the data 70 with the value of I that is at second position we want to add. This is currently what we have, right? So what is the first step that we did? We created a new node. I created a new node. New node is of this form. It has the data 70 and the next as null. Let's consider its address as 800. Now this is what I have. Now I created a new variable that is temp. The value of temp is initially equal to head, so it is 100. So what I am doing is I am maintaining this loop while count is less than I minus 1. I am doing temp is equal to temp arrow next and count plus plus, right? ठीक है जी. तो initially the value of count is 0. So I'll check for if count is less than I minus 1. If count is less than I minus 1, that suggests that 0 is less than 2 minus 1. That is 1. That's true. We'll go inside the loop. We'll make temp is equal to temp arrow next. Temp key value changes to 200. Right now temp value is 200. That is I am here. Right, and the value of count increases to 1. As soon as the value of count increases to 1, we'll again check for this while loop. Now 1 is not less than 1. We'll not go inside the loop and our thing is done. We just want to be here. Now we are here. We have reached till this point, or the one index less than the actual position, and this is 0, 1, 2, 3, 4, right? We want to insert between 2 and 3. So we have reached till here. We have a new node 70 and we want to insert it here. So what can be the possibility? We can simply put can we do this like temp के next में we can put this new node, right? Can we do this? Like if it is, let me just create it once again so that you can get some more clarity with addresses. Right? If you have something of this sort, ठीक है, यहाँ its address is 100, its address is 200, it's 300, it's 400, it's 500. 200 is stored here, that is the next address. 300 is stored here, that is the next address. 400 is stored here. We want to insert a new node that we have created. Its address is initially 800, its value is 70, and this is pointing to null. We have reached till here. Now temp points to 200. Temp is currently pointing to 200, and now we want to insert. So the one thing that we can do is we can remove this 300 and we can add 800 here. That makes this connection, right? But as soon as we do this, we lose this 300. We don't have the rest of the linked list available, so we'll not do this. What we'll do this before making this connection, I'll do one thing more. I'll store this 300 somewhere, right? I'll create a new pointer that is node star a, and I'll store this 300. Node star a will contain my temps next. So now this value is safe. This 300 is safe in this node star a. Now what I will do is, now I can do temp ka next is equal to new node. This line makes this 300 to 800, and now this new 100 this new node's next should point to this. So this address is stored in a. So what I can do is I can do new nodes k next is equal to a. So these three statements we need to perform in order to insert this node. Also, one thing more, like instead of saving the address here, what we can do is we can do this in two statements also. So doing this in two statements is of this particular form, like rather than first making this connection, if we make this connection first, right? So what I will do in this case is new nodes next should contain temp next, right? This will be of this will be like let me just take you through it once again. This is 300, this is 300, and what we are doing is this is null. So I'll not make this connection first, I'll make this connection first. So I'll put new node के next में 300, new node के next में temp का next. 300 is stored in temps next, temp is here, temp के next, right? And once this is done, what we'll do is we'll do temp के next में new node. That is, this 300 will be cut to 800 and this connection will be made. So we can also do it in 2 steps, we can also do it in 3 steps, right? Let me just take you to the code part and then you will understand it better, right? So we are here. What I want to do is I want to write 3 statements. Node star a is equal to temp arrow next. That means it is storing, it is saving that thing. Next is new node, sorry, temp के next में is equal to new node is equal to new node, and new nodes next will be having a. So these 3 statements will solve the purpose or serve the purpose, right? Let's just try and see if this is working and how it goes, right? So we initially created a linked list that is having 5 nodes, 1 2 3 4 5. They all are connected to each other. We are printing linked list using the head, right? Let me just try and run if to see if it is working. So yeah, this is working fine. We have got 1 2 3 4 5 as our output. Now what I want is I want to call this function insert node. So insert node and 3 arguments, right? We are passing on head, we'll pass on this head, we'll pass on the data, let's say I'm adding 70, and I, that is the second position. So these 3 things I have passed. I'm again printing my linked list, print linked list, and I'm again passing the head. So we'll check if this insert function is working correctly or not. Before that, let me just call cout endl. So yeah, we have 2 linked lists, 1 2 3 4 5. 70 is inserted at the ith position and we are done. So we have successfully inserted a new node in our linked list, right? Now let me just try out something else. So instead of 2, let's say I make 7, make it as 7. So now you can see we are getting a runtime error. Why we are getting a runtime error? Because 7th index does not exist. We have a linked list with only 5 nodes. So how this operation will be performed, right? Let's just see this. So what we are doing in this case is we have this linked list 1 2 3 4 5 and null. I am passing on the head, it's going to temp, its value is, let's say, 100, 200, 300, 400, 500, and initial value of temp is 100. New node I have created, the value of new node is 70 and it is null, right? This is something that we have in our hand currently. Now I'll check for the value of count is 0. I'll check if while count is less than I minus 1. Now the value of I is 7, right? 7 minus 1, that is 6. Yes, count is less than 6. I'll go and make temp is equal to temp arrow next. It will become 200 and we'll do the value of count. It was initially 0, we'll make it 1. Again, I'll check for the value of count. Is it less than 1? Yes, it is less than 1. I'll make it as 2. I'll increase the value of temp to temp arrow next. That is, it becomes 300. The value of count becomes 2. Again, this happens. We'll check if 2 is less than 6. Yes, 2 is less than 6. What I'll do, I'll make the value of temp is equal to temp arrow next. It will become 400. 2 becomes
3. Again we'll check, it again goes, we'll make it 500. Again it will become 4. Yes, 4 is less than 6. Again we'll make 500 as 600. Will we make 500 as 600? No, we'll make it as null because 5 के next में it's null. So the next time we have the value of temp as null and we are accessing null is the next. So null's next is not defined. It will give us a segmentation error. So to solve this purpose, what we'll do is we'll make a check. We'll make a check until and unless temp is not equal to null, then only we'll perform this thing. So what we are going to do in this case is we are going to make a check and temp is not equal to null. So if this condition is there, then probably we'll get to our answer. Here also we'll make the same check. If temp is not equal to null, right? So we have finally checked this edge case also. Okay, if at any point we pass on a number which is out of the size of the linked list, so what will happen? So now we'll try to run. So yeah, you can see we have the same linked list, 7th position we don't know only, so how we'll add anything there, right? So this is something that we have solved right now. One thing more that I would like to stress upon, if I pass on my position as 0, right? Let's see. So your expected output should be, according to you, it should be 1, 2, 3, 4, 5. This is the current linked list. So if I have 0th position, so it should be like 70, 1, 2, 3, 4 and 5. Null, right? Let me just try and run to see what happens in this case. So now in this case, you can see 70 is being added at the first position. So why this is happening, right? Let's just try and see why this is happening. Now if I am passing head 70 and 0, so head data is 70, I is 0. So first thing what we are doing is we are creating a new node. We have created a new node already, 70, and this is null, right? Now we are creating time count value is 0. We'll check if count is less than I minus 1. So what is I? I value is 0. So we are checking if we are checking for the first condition, that is count is less than I minus 0. So this is wrong, right? 0 is less than minus 1. This is wrong. So we'll not go inside this loop. We'll directly go inside this loop. So what happens here is we'll create a new node, that is node star A is equal to temp ka next. So temp's next is, that is 1 ka next, that is 2. So A will be having A's next, that is 200. A will be having 200. Now temp's next is equal to new node. Temp's next, that is 1 ka next, will be equal corresponding to this new node. So 1's next will correspond to 70 and we'll do new nodes next is equal to A. So new nodes next will point to this. So my linked list according to our code will look something like 1, 70, 2, 3, 4 and 5. But this is wrong. So we need to make a separate check. If at all the value of I is equal to 0, what I need to do is I need to simply put new nodes next is equal to head. If I simply put this new node ka next is equal to head, matlab 70 is next, I point it to this and I make this new node as head, then it will serve the purpose. So let's try and see in the code how it looks like. So we'll make this check first of all. If I is equal to 0, what I will do is I'll simply put new node k next equals to head, then head should point to the new node, right? This is what we need to do. But in this case we have changed the head itself. That means in our original linked list the head was something different, but we have changed the head here. So rather than using this, we'll try to return our head, return our new head. So if we are returning something, so this will also change. It will change to node star, right? And also for this particular function nothing is going to be changed. We just need to return head. Everything else is remains same. Here we need to change our head, and I think we are done. Right now we are again passing 70, 0 and head. So now 70 should come at the first position as per our code. So yeah, 70 is coming here, and we have successfully solved this problem. So this was basically how we are inserting a number at ith position in our linked list. Right now we'll see some more operations on linked list. So now we have seen one operation, that is insertion. Now let's just talk about deletion. Right, if you are given a linked list, let's say of this particular format, 1 2 3 4 5 and null, and somebody asks you to delete a node from this linked list, right? They give you the position of the node to be deleted, similar to what we were doing in insertion. So position में जैसे तुमको दे दिया है उन्होंने, let's say 2, right? So you want to delete the node at the second position. So to delete the node at the second position, that is, this is the first 0th node, first node, second node, third node, fourth node. That means you need to delete this node, that is third node. So what we simply will do in this particular case is, let me just make it like this. We have something like 1, right? We have something like 2, 3, 4, 5 and null. Right, so let's say the head is 100, it is 200, 200 will be stored here, 300, 300 will be stored here, 400, 400 will be stored here, 500, 500 will be stored here, and null will be stored here. We want to remove this node. So what we simply will do is, rather than making the second node, that is 0, first, second, third, fourth, the first node to point to 3, we'll make it point to this, and we'll explicitly delete this. This is what we are going to do, right? So what the first step in this case would also be, we'll traverse till the I minus 1th node. Second thing is, what we'll do, we'll first of all we'll make a new node, let's say node star A, and inside this node star A, what I'll store temps next, that is this address. I'll store 300. I'll create another node, that is node star B, and inside B I'll store A's next. So A's next is, that is 300 next, that is 400. So in B we have 400 now, in A we have 300 now, and what we want is, we want to put 400 here. So what we'll do is, we'll do temps next is equal to B, and these 3 steps will finally delete this node. This will start pointing to this, and this will be explicitly removed. If we have made the nodes as static, then we don't need to do anything. If we have made the nodes as dynamic, then we need to use a delete keyword and delete them explicitly, right? Also, one thing more, like how we'll handle the case of if we give the node position as 7. Same, we'll check for if temp is not equal to null. This is the condition that we checked in insertion also. One thing more, if the node position is 0, so what we simply will do in this case is, head is equal to head ka next. This is what we'll do in this case when the position given is 0. Right, let me just take you to the code and see how it works. So yeah, so this is the code for insert node. I'll see if we can just make some modifications in this code only, and we'll get to our answer. Right, I'll copy and paste this entire node once, this code once again. Instead of insert node, let's just name this function as delete node. Now I'll not be having this data part, I'll just have the position of the node, right? I don't need to create any new node because I'm deleting a node. I'll make this temp variable, I'll point this temp to head, count variable will also be made for this 0th position. For if a node is at the 0th position, what we were doing, right? If this is the case, this is the linked list, and we want to delete the node at the 0th location. So this is initially pointing to head, so we'll simply do head is equal to head arrow next, right? and we'll return. So we'll rather than doing this, what we'll do is we'll remove these two lines. I'll do head is equal to head arrow next, and I'll return head, right? This will remain the same because we are moving on to the I minus 1th loop. Once temp is equal to I minus 1th loop, these three steps are what I am going to change. So node star A will be equal to temp cut next, right? Node star B will be equal to A ka next, and in temps next I am putting B. That's it, right? So what I am doing in these steps is, in these three steps, what we are doing is, like, we have this case 1 2 3 4 5 6 and null. This is 0th, 1st, 2nd, 3rd, 4th, 5th position. I am adding, I want to remove this, delete this 2nd node, right? So now temp is pointing to currently this, and the value of temp is 200 now. Its address is 300, its address is 400. I am doing node star A is equal to temps next. So temps next is now storing 300. So A will store 300. B will store A's next. So A is 300. 300's next is 400. So B will store 400. And temps next will point to B. That is this 200. This 2's next will start pointing to this 400. That is B. So simply this will be removed. And I hope this should work. Right? Let's just try and run this code. This is delete node. Let's just create one more function, that is delete node. Let me insert head, and let's say we'll remove this 70, right, the 0th location one, and then we'll do the same printing, right? Let me just run this code. So yeah, the 70 is removed. That is the node that was at 0th position, that is now removed. Something more we can try, rather than 0, we are removing the node at the 2nd position now. So now the node at the 2nd position, that is 2 is removed. 0th, 1st and 2nd, the 2 is removed. Let me just make it as 7. 7th is the index that does not exist. So we'll check if that condition, that case is handled. Yeah, that case is also handled because 7th is not the position in this linked list, and that we can't delete anything. So I hope this was also easy and you have got a pretty good idea of how to insert a node in a linked list, how to delete a node from a linked list. Let's see some more things in linked list going forward. So now we have seen insertion as well as deletion in a linked list. Now that was without using recursion. Now recursion is a very important concept, and going forward we'll be using recursion to solve problems related to linked list in many ways, right? So I want you people to understand how we can insert or delete a node using linked list, or a node in a linked list using recursion. So this is something that I want you to understand now, right? So what happens in recursion? We will basically be looking forward to 3 things in a recursion question, that is a base case, a small calculation that we perform, and a recursive call, right? So let's just take one example, the same example that we were taking for so long. 1 2 3 4 5 and null. So this is the linked list that is given to us initially. Now I have 2 things, that is I have data. Let's say I want to add a node with data 70, and I, that is position is 2. I want to add a node at position 2 with data 70. This is 0th index, 1st index, 2nd index, 3rd index, 4th index, right? So I want to add the node 70 here. That is my node should my linked list should look like 1 2 70 3 4 5 and null. This is what I'm looking forward to, right? This should be my output, right? So how we'll go forward doing this particular question is, so what happens in a recursion question? So whenever we are given a recursion question, we first think of the base case, right? This is the linked list that we initially have. So what will be the base case? let's say if the head is only given to us as null, if at any point head is equal to null, so we can simply return null. What we'll add in a null linked list, right? We don't have any position to add in that linked list, so we'll simply return null. So this will be my base case. Also, what happens in any recursion problem is we try to break the problem. We try to break it into in such a way that we have a smaller part and there's a large part. So let's just try breaking it in this way, so that we perform on this smaller part and recursion gives us the answer by automatically doing the things for the rest of the part, right? So now if this is the linked list, right, this is the part that we are concerned about, that we will have to perform a small calculation on, and this is the part that recursion will help us to, like, if there is something to be added in this part, then recursion will give us the answer, right? So what we'll focus on while solving this particular problem is that, for one, right, so we want to, if we want to add any node at the first position, so what will happen, right? So if the value of I is equal to 0, that is I want to add the node at the 0th location. So what will be my step? So first step is, if I want to create a new node with data 70, I'll create a new node. So first step is creating a new node, right? After that, what would be the step? I will add the new node at 0th position, right? So my first thing is I'll create a new node, that is node star new node. I'll do new node with data 70. Now I have this new node. So at ith position, what will happen? We'll simply do no new node next will point to head, right? We'll make a new node and we'll make it point to head. Second thing in this, what we'll be doing is we'll be updating our head. Now our head will be equal to new node, right? My head points to this and will return head. So if we are to add any new node at the 0th position, so these are the 3 steps that we'll perform, right? Yeah. So after this, we need to call on recursion, right? But like, this is what we will do if we are to perform at the 0th position. Now we are to perform at the 2nd position. So we'll want recursion to do that. We'll make a recursive call, that is delete recursive, insert recursive, and we'll pass on 3 parameters. So which parameters? Firstly, instead of head, now what we'll pass on? We'll pass on head ka next, because we are passing the entire linked list except the head. So we'll pass on head ka next. We are breaking our problem basically, right? Data will pass as such that we want to add, and now the position, right? If let's say I have 2nd position, so this is 0th, 1st, 2nd, 3rd, 4th. So this would be my 2nd position in that case, right? But now this part is already done by us. Now I'm passing this particular node. So for this particular node, what will be, so these will be the indexes 0, 1, 2, 3. So in actual, we want to add at the 2nd position, but in our new node, it is the first location, that is I minus 1, 1 less than 2. So that is, we'll pass on I minus 1 here. And after this, we'll store it in a new variable, that is node star x. So this x will give me updated linked list with addition of 70 here. So this x will have now 2, 70, 3, 4, 5. Now x is having this. Now the last thing that we need to do is we need to connect our head with this x, that is heads next should point to x. Now we have our complete linked list with head as the operated head, and we'll simply return this head. Let me just explain it to you once again in a little more simpler way so that you can get an idea. So what we're actually doing in this particular question, we are to add a node in a linked list using recursion, right? We are given this linked list. We are given head is here initially. We are given the data as 70. I as 2. That is, we need to add a number at the second position, 0, 1, 2, 3, 4. Right? Now first is base case. So we have seen that base case would be if head at any point becomes equal to null, so we'll simply return null. Small calculation is like, I'll do the small work, we'll break the problem into two parts. This part will be handled by recursion, this part will be handled by me. That is, at if at all the position is 0, then what I'll do is I'll create a new node. Right, this new node will be created. What I'll do for this particular case is I'll do new nodes next is equal to head. Right, and I'll update my head equal to new node, and I'll return this head. Right, these three things I will do. What after this? So we have done this, we have performed the base case, we have done the small calculation. Now it's the time for recursive call. So what happens in a recursive call is, so now it's the time for recursive call. Insert recursive. So here are the three arguments. Initially we were passing head, data, and I. Now what will pass? I have 1, 2, 3, 4, 5 and null. So now this is our breaking point. We have performed the operation on the first, that is the head. Now we need to pass this into our recursive function. So this will be, instead of head, will pass on head ka next. Data will be same. Now carefully observe what will happen here. Now initially it was, indexes were 0, 1, 2, 3, 4, right? So we were to add at the second position, but now we are passing this as our linked list. So its indexes will be 0, 1, 2, 3. Instead of this 2, now we have 1 that is to be passed. That is one position prior to my actual position. So we'll pass I minus 1 instead of I. I'll get this in a new node, that is node star x. I believe this x will contain my 2, 73, 4, 5. This is something that recursion has done for me, right? It's stored in x. Now the only thing that is left is I need to connect my head with this x. Head ke next mein I want x. So I'll add on 1, 2, 73, 4, 5, and this will be stored in head. I'll simply return my head. This is how it looks like when we are performing insertion using recursion, right? Let me just take you through the code part. So yeah, let's just create a new a function, that is node insert recursive. Here we'll have node star head, we'll have int data, we'll have int I, that is the position. So the first thing that we do is we'll create a new node is equal to new node with this data. Right, I've created a new node. After this, what we are going to do, if we are to perform this in a recursive manner, is the first thing that we'll do if we are to perform this in the recursive manner is we'll check the base case. If at all my head is equal to null, then what I'll do is I'll simply return my head, that is null, right? After that, so we are to perform the small calculation for a case if I is equal to 0. If the value of I is equal to 0, then what we are going to do is we are going to attach this new node in the front of my linked list. So new node ka next is equal to head. We'll update this head also. Head is equal to new node, and I will return head. These are the things that we are doing for our case. Next is the recursive call. I'll get the answer of this recursive call. What are the parameters that I'll pass on? I'll pass on heads ka next. I'll pass on the same data, and this is very important, I minus 1. Right now we have x, we have head, so I simply need to connect head ka next is equal to x, and I will return my head. I hope this should be fine with you. So let's check if this is fine. What we are actually doing is we are creating a new node. This is like, this node is being created 70 and null by this particular line. We are checking for if the head is equal to null. This is the base case. We are doing the small calculation for this part of my linked list. For this part, I am doing this work. If I have to add a node at the front location, then I'm passing on the entire linked list in a recursive call. Instead of head, we are passing head ka next. We are passing the same data. We are passing I minus 1. I minus 1 means the position that is prior to the actual position, because we are passing head ka next, right? So now this x will hold on by adding the number at this particular position. I'll simply connect this head ka next equal to x and will return this updated head. So this is how we perform insertion using recursion. Let me just see if this runs well. Right, insert recursive is what we need to call upon. So instead of node insert node, what I'll do is I'll call upon insert recursive. So let's see if it adds upon, instead of 70, let's say I give 69 this time. So yeah, you can see 69 is added at the 4th position. Let me just change this index to 0. 69 is added at the 0th position. So recursion is able to help us in inserting a node in our linked list, and the code looks a little more simpler, right? So let's just see how we can perform deletion operation using recursion, right? We have already seen deletion using a normal method. Now we'll try to see deletion using recursion, right? Yeah. So now what we have is, it's very similar to what we have seen in the case of insertion. We have this linked list and somebody tells me to delete the node at the ith position, that is 2nd position. So this 0 1 2 3 4. So somebody tells me to delete this node. My linked list should be, the output should be something like 1 2 4 5 and null. This is the output that I want. Right now currently I have this. So how using recursion we can do this? So again, we'll have three things in recursion. So which all 3 things we are concerned about? First is base case. Base cases, we'll check for if my head is equal to null. If it is, we'll simply return null. Second thing is small calculation. So what will be the small calculation? That is if the value of I is equal to 0. That is if I want to remove this head. What I will do is I'll simply do head is equal to head ka next. That is, my head will start pointing to here, and I'll return my head. This will be my small calculation. What will be my recursive call? So recursive call will be, I'll take a variable, I'll take a node x, node star x, and inside this node star I'll call recursive, that is delete recursive. I'll pass on 2 parameters, that is I'll pass on this part of my linked list, that is head ka next. Instead of I, again we are passing I minus 1. I hope now this is clear why we are passing I minus 1, not I in this case. Right now we have x also, we have head also. We need to connect both of these. What we'll do is head ka next equals to x and return head. This is what we are looking forward to do in this particular question. Let me just take you through on how we will be performing the deletion operation. Right, let's just try and see if we can copy paste this only and make some changes to get the answer. It will save your time as well as my time. So instead of insert recursive, I'll use delete recursive. We should pass head. We don't need data this time. We don't need to create any new node this time. We'll simply check for this, the base condition will remain the same. For value I equal to 0, we'll remove all this. What we simply need to do, head is equal to head ka next. We have simply removed the first node. I'll return head again. Right now we'll call upon the x, that is insert delete recursive. Here it will become delete recursive. I'll pass on head connects. I'll remove this data as a parameter. I'll pass on I-1 head connects. I'll put x and I'll return my head. This will be the perfect function for delete recursive as well. Let's just try and see if we can how it goes here. So instead of insert recursive, what I'll do here is delete recursive. Head is same, 69 is what I need to remove. I want to remove the number that is present at the 0th location. So let's see how it goes. Yeah, so we have successfully removed 69, that is the number at the 0th position. Let me just change the index to 4 3. So we have removed the number that is present at the third index, that is 0th, first, second, third index is 3. So we've successfully removed the number that is present at the third index, and these both are working super fine. So we have been able to successfully insert as well as delete elements from a linked list using the normal operation as well as using recursion. Going forward, we'll be solving a lot of questions using recursion, so make sure you do these questions on your own. Make sure you use a copy and pen and try to dry run these approaches so that you can get a better clarity on how you can get inside this very, very interesting topic of linked list, right? So the next thing that we're going to understand is basically calculating the length of the linked list, right? We are going to see how we calculate the length of linked list. So let's say we have this particular linked list 1 2 3 4, and we'll try to see the recursive solution for the same, right? So what happens is, in a recursive solution we need to check for the base case first, right? So base case would be if the length is equal to 0, if the value of head is equal to null, that is linked list does not exist, we'll simply put length is equal to 0, else we'll break it here, and this is something that will pass on in the recursive function. That means our recursive function will return the length of this part, and we'll have to do this small calculation, like what for this part we'll have to calculate. So for this part, what is the answer? Like it is of length 1, so we'll add 1 in this. So overall it would look something like length function, and we have node star head. So what we'll do is we'll check for base case. If head is equal to null, we'll return 0, and we'll simply return 1 plus, we'll call the recursive function and we'll pass head connects. That's it. This will give us the length of linked list, right? Now there is one more thing, like I'll try to code this also, but before going forward, let's just discuss one more concept, that is how to calculate the middle of our linked list, right? Calculating the middle of linked list. So it is very, very simple. Like we have already discussed how to calculate the length of the linked list. So calculating the middle is no big thing, right? Let's say you have this kind of a linked list, right? So you have to calculate the middle of the linked list. So using the above function, you know what is the length of the linked list. So the length of the linked list is 5. Length comes out to be 5. So what you can do is you can simply find out the mid. Mid will be equal to length by 2, right? Length by 2, that means 5 by 2, 2. So it will be 0 1 2 3 4, right? So this is the index that will be our middle index. So we'll simply return the data that is present at the middle index. Let's say our linked list is even linked list, like the length is even. So how we'll find out the same? Let's say we have 6. Now 6 by 2 is 3 again. So we can find out by 0, 1, 2, 3, 4, 5. So the third index, that is the second middle. Now for an even linked list, we have two cases, right? It can be either the first one or the second one. So for calculating the second one, we can simply use 6 by 2 and we can return. But this is again a little bit of more complex. Let's just try to simplify this, right? So simplifying this is a very important technique that is basically known as hare and tortoise method. So what is there in hare and tortoise method is how we calculate the length of the middle of the linked list. We are given a head of the linked list. We initialize two pointers, that is node star slow and node star fast. We initialize them to head. Let's take this example. Now this is my head initially. I created a slow pointer, I created a fast pointer, both point to this head initially, right? Now what I will do is I'll move the slow pointer one step at a time. Slow is equal to slow's next, and I'll move the fast pointer as fast is equal to fast's next, right? So in the first step, slow will come here and fast will come here. The next step, slow will come here, fast will come here, right? So for whenever fast reaches null or a number before null, that is whenever this thing becomes null or only fast becomes null, so then we can't access this thing at all, so we will not go. So we'll put up the condition. So whenever this fast will point to either null or one less than the null, then the number that is there at the slowest node is my middle. I'll simplify it when you will do the code. That will make the things a little more clear to you, right? So what actually we are going to do is we are going to put down the condition here, and I'm going to move slow by a single time and fast by 2 times, right? And I'll return the slow pointer. So what should be this condition? So there can't be a time when fast ka next is equal to null, right? Fast is not equal to null and fast's next is not equal to null. As soon as fast's next becomes null, so we can't access this. Hence, this will give a segmentation fault otherwise. So we can simply return the slow pointer, right? So this is something that is an approach that you should keep in mind. You can categorize it for even and odd linked list as well. Now let's just move on to the code and see how we'll code this particular question. So now let's see the code part of this. We have a linked list. Let's first find out the length. For this, the return type will be integer only, and we'll be passing on the head, right? So first thing is if head is equal to null, so we'll simply return the length as 0, right? Else what will return? 1 plus length of heads next, right? This is what we discussed. So probably this should give us the correct length. Let me just find out length is equal to length of my head, and I'll see out endl first and then length, right? Let me see if we can get the correct length. Yes, we are getting the correct length, that is 6. So this linked list is containing 6 elements. Now let us just find out the middle also. So its return type will be node. Let me just name it as middle only. Node star head. We are passing on the head. And how will calculate the middle? The first thing is, let me just take a temporary node. Let's just not mess around with the head. We'll take a slow pointer that is initially equal to head. We'll take a fast pointer that is also equal to head. We'll run a loop while head is not equal to null. Sorry, let's just write this condition later on. First thing is slow is equal to slow's next is what we are going to do. Fast is equal to fast's next, right? And we'll return this slow pointer. So here the condition should be, firstly fast should not be equal to null and fast's next should not be equal to null, right? These are the two conditions that we have. Let's just find out the middle as well. So let me just have this as node star mid is equal to middle. I'll pass on the head again. I'll see out mid, and that's it, right? Let's see what does the answer. Mids data, right? This is a node, so we'll be finding out mids data. So yeah, so the middle number out of this list is, we are getting the second middle, that is 3 as the answer. We can also get the first middle if, let's say, you are given the same question and you need to find out the first middle, right? In this particular linked list, you need to find out the first middle. So this is the question for you to try, think upon it, do a dry run and try solving how to get the first middle if the length of the linked list is even. Let's also try for an odd length linked list, right? Let me just remove this insert recursive. So now let's see what is the answer that we get. So yeah, so this is the linked list that we have. The length of the linked list is 5, the middle that we're getting is 3, and I think we are all set to go with the next questions. I hope you have understood finding the length of the linked list, middle of the linked list, insertion, deletion recursively as well as with a normal method. So this creates the base for you to move ahead with other questions. So we'll talk about other questions now. So now we have very well discussed what is a singly linked list. So now I want to just focus upon what is a doubly linked list and how can we uh, operate on a doubly linked list, right? So when I say a singly linked list or a linked list in general is what we say. Singly linked list, it looks something like this: 1, 2, 3, 4, 5 and null, right? This is what a singly linked list looks like. It just has the forward arrows, right? But what happens in a doubly linked list is the structure is something similar to this. 2, 4 and 5. So it is something like this, right? So in this case we had the node structure as, our node was something like, we had int data, and node star next. So this was basically the components of a singly linked list or the data members of a singly linked list. But in doubly linked list, what happens is, along with this next pointer, we have something known as previous pointer. So what is the benefit of this is, like, at any point we don't need to like, we can access the previous element to that also and the next element to that also using any particular element. So the node in this case would look something like int data, node star left, and node star right, or you can say them as next or previous, right? Nodes are next, nodes are previous. So this pointer points to the next node, this pointer points to the previous node, right? So now let's say you are given a case in which you need to remove this particular node, right? You are given a node, let's say A, and this points to this fourth node, and you need to remove this particular node from the linked list. How can you do it without traversing the linked list at any cost? Right? What we need to do, we simply need to put this here, and we need to put this here, right? And this we need to explicitly delete, right? Now let's say this is the node that is given to us. The node is node star A, right? This is the node that is given to us. Now what we'll do is we'll do A's previous. So what is A's previous? A's previous, it's 3, right? And 3's next, right? 3's next, that is A's previous next. So A's previous is 3 and 3's next is this. So what we want to put in this is we want to put 5. So what is 5 with respect to A? So this is A, so this is A's next, right? So we can say that A's previous ka next is equal to A's next, right? This is the first line of code. Now after this, like this connection has been made. We have successfully made this connection, right? Now this connection we want to make it again. So how we'll do that? So now again, so what is this node? So this is A's next. A's next is this. Now iska previous, A's next previous is equal to A's previous, right? What is A's next? A's next is 5. So 5 ke previous mein what we are putting? A's previous, right? So these 4 lines of code are something that will help us in this particular case. So this is how a doubly linked list works. Apart from that, let us just go through what STL and lists look like, right? So how, like for every time when we are solving particular questions, we don't explicitly create linked list. So we know something known as linked list STL. So STL, you all know that it is standard template library. So what happens in linked list STL is linked list STL, it is categorized into 2 parts. One is forward list and one is only list. And we need to specify the data, like the type of elements that we want in this list, whether it's integer or whether it's something else, right? So this is known as doubly linked list. This list corresponds to doubly linked list. And this forward list corresponds to singly linked list, right? So let us just have a more closer look at forward list and list through our website. Like there's a website known as c++.com through which you can get entire information about all the STLs. So you can see forward list, they have mentioned it very, very clearly what forward list is. Forward list are sequence of containers that allow constant time insert and erase options anywhere within the sequence. So there are a lot of pre-built functions, pre-built member type functions that are already defined so that you can use them directly. So these are the operations, right? You can use insert after, you can use erase after, you can use remove, unique, merge, sort, reverse. Different functions are there that you can use with forward list. Similar to forward list, there is an STL known as list STL. So list STL also, it has some of the functions like begin, end, and some others. So make sure you check out c++.com for more information about STL on linked list, right? You will get entire information about all different kinds of standard template libraries that are available in C++, right? So now let's see how we can use them in our questions ahead. So the next very famous question that you all might know about or might not know about is reversing a linked list. So you all might have heard of an ad. Do you know how to reverse a linked list? So I hope you all know this, right? So reversing a linked list, what happens when we have to reverse a linked list? We are given such nodes like one. We are given this linked list, right? 5 and null. And you need to reverse this linked list. Like let's say its addresses are 100, 200, 300, 400, and 500. When you'll reverse this linked list, it will, like, it should not become something like this. Let me just write it down and show it to you. It's not that you are just taking out 5 and putting 5 here, or taking out 4 and putting 4 here at the same address. No, this is not to be done. Instead, what you need to do is you need to change the connections. How you will change the connections? That is, if 4 is pointing to 5, now 5 should point to 4. If 3 is pointing to 4 here, now 4 should point to 3. If 2 is pointing to 3 here, now 3 should point to 2. If 1 is pointing to 2 here, now 2 should point to 1. 1 is pointing to nothing, then 1 should point to null here. And you need to return this head. This null will be removed. So this is what is our aim. This is what is the output that we are expecting, right? So this is what we are looking forward to in this particular question. So how we'll do this? There are two particular methods that we'll see to implement this particular question. One is iterative method, and the other one is recursive method. So we'll see both methods. Let's start by iterative method so that you can understand the in-depth analysis of how we are reversing a linked list, right? So what happens in this case is, in an iterative case, let's say we have this linked list 1, 2, 3, 4, 5 and null. We have this linked list, right? Let's consider its address as 100, 200, 300, 400 and 500. So now let us say what we want to actually do. We want to reverse this pointer. That is, if this is the head node, right? So heads next, now this is currently pointing to 2, right? Now we want to make this 2 to point back to 1. This is what we want, right? So let's consider 3 pointers. We can solve it using by taking 3 different pointers, right? So let me just mark them as, so this is my current pointer. My current pointer will be here. I'll take a previous pointer. My previous pointer will be here, and next pointer, that is my next pointer, will be here. So this is my current number, this is my next number in the linked list, this is my previous number. So for the first case, the previous should be equal to null because there's no number before 1, right? Now what we are actually trying to do is, in this case, is what will be C's next. So we want to connect this one, instead of 2 we want to connect it to null, right? We want to put C's next as null, right? We want to put C's next as null. So instead of null, like now we have previous, but every time when we'll, let's say this is the current situation, let's say P, C and N are here, right? So now what you want to put in 4's next we want to point to 3. So C's next we want to point to previous, right? So this is one thing that we'll do. So we'll point C's next to previous, right? After that, what we'll do? We'll move on, right? We'll move on this entire thing to the next part. Now current will come here, previous will come here, and next will come here, and we'll repeat the same cycle, right? Now what we have done in this case is, after C's next is equal to P, we have made P is equal to C. previous becomes current, and C is equal to N. Current becomes my next, right? And what happens to the next? Next has changed to from here to here. That is, next is equal to N ka next, right? And like we will be putting a check in front of the N, because as soon as we move ahead in our linked list, at some point of time N will become null when current will be at this particular position. So we can't access null ka next. This will give segmentation error. So I'll put a check if N is not equal to null, then only we'll do. So these are the three conditions that will help us reverse the linked list, right? And what we'll simply do once we reach till here, we'll simply return P at the end, right? So these are the steps that will follow. Now let's move on to the code. I hope you will better understand it using the code. So this is a question that is there in front of us. It is basically reversing a linked list. We are given the head of the linked list, and we will be performing. So first thing is will check if our head is equal to null. If our head is equal to null, we don't need to do anything. We just simply return null, right? After that, what we took 3 pointers, list node star p, that is previous pointer, it was initially pointing to null. We also took list node star c, that is currently pointing to head. We took list node star n, that is currently pointing to heads next, right? These are the 3 things only we have. So now we were repeating the steps again and again until and unless C becomes equal to null. C is not equal to null. So which all 3 steps were we are performing? C's next becomes previous, then previous becomes my current, and current becomes my next. These are the 3 steps, and the last step was if n is not equal to null, we will be moving n is equal to n's next. So these are the steps that we were doing actually, and what will simply return. So my last will be pointing to what? The previous one. Let's just see how it is. So what we have done in this case is we have created, so first of all we have been passed a head, right? Let's say this is the linked list that we have 1 2 3 4 5 and null, right? I have made 3 pointers p, c and n. P is here, C is here, N is here, right? C is at the head, N is at heads next, and P is at the null, right? Now we'll run this until C reaches here, until current reaches here. So what we are doing, C's next is equal to P. C's next is equal to P. That is C's next. One's next is equal to P. So it is null. One's next becomes null, and what happens next is previous equals to current. Previous becomes current. So previous comes here. Current becomes next. So now current becomes next. And if null is n is not equal to null, n becomes n's next. So this n becomes n's next. That is n comes here, right? Now again we'll move on to the loop. C is not equal to null now also. So what we'll check, C's next is equal to P. Now C's next is equal to P. So what is P? 1. So we'll make this connection. That is 2's next. So 2's next is pointing to 1 now. This is we have done. P equal to C again. So now this becomes P. This becomes C. N is equal to N arrow next. So this becomes N. Again we'll simply run. We'll move here. We'll move these 3 things 1 step forward. This becomes N. Now again for this it becomes like this. We'll move again. This becomes P. This becomes C. N becomes null. Now at this point N becomes null. So we'll not be moving. We'll not be performing this step any forward, right? And we will simply now in the next step, C is still not equal to null. We'll again run the loop. C's next become equals to P. C's next, matlab 5's next becomes equal to P. 5 starts pointing to 4. Present becomes current. So now this becomes P. This becomes C. So now 5 is pointing to P, right? P is pointing to 5. That is the last node. That is the head node. We need to return this only. We need to return this linked list, right? 5, 4, 3, 2, 1 and null. Now p is pointing to 5, so we'll simply return this 5 in this case, right? I hope this is a little more clear. I would say try to dry run it on your own on a piece of paper. You will understand it a lot better, right? Let's just try to run this code. So yeah, so 1 2 3 4 5 linked list was given to us, and we have successfully reversed this linked list as 5 4 3 2 1. So this was the iterative method of reversing a linked list. Now let's see how we can do it using recursion. So recursive method is also very simple. You just need to understand a little bit the steps of recursion basically, right? So which all steps of recursion do we know? So in every recursion question, we first we take care of the base case, we take care of the small calculation, and we take care of the recursive call, right? So in this question also, let's just say, yeah, so in this question also, recursive solution, right? So we have this linked list 1 2 3 4 5 and null. So what happens is we try to break our problem in recursion, right? So if we'll break our problem from here, now this is one part, this is one part, right? So this part basically is something that will pass on to recursion, and we expect recursion to give the correct answer. What we expect from recursion is recursion will give us this 5 4 3 2 and null with this as the answer. That is, this is the answer that is coming from recursion. तो हमने सोचा कि recursion should give us this, right? After this is done, now what is the thing that is left on us? Now we have this head, right? We want to point this 2 to this head. We want to point this 2 to this head and this head to null. So these are the two steps that we need to perform, right? So what is 2? So 2 stands for, matlab, if this is the head, currently this is pointing to head. So 2 is what? What is 2? So we want to make 2, we want to point this 2 to 1, right? So now head points to 1. So what is heads next? Heads next is 2. So we want to point this 2 to 1, right? We want to point this 2 to 1. We want to point this heads next to well, heads next is 2, and we want to point 2's next to 1 again. So heads next is 2, we want to point 2's next to head again, that is 1. So now this connection is made. This is a very important line. Heads next is equal to head. This line is very important. What we are doing in this is heads next is 2, 2's next is 1. This is what we are putting. 2 ke next mein we are putting 1, 2 ke next mein we are putting 1, right? After this head, so head should point to null, so we'll write head is equal to null. These are the steps that we need to perform. Also there should be one base case. So what should be the base case? Like this recursive call, when it should return, when the value of head ka next becomes equal to null. When heads next become equals to null, we simply return head, right? This will be my base case. Now let me just try to submit this recursive code also and see how it goes, right? So let me just create one more function, list node star reverse list node star head, right? What we'll put inside this is, we'll make a check, like this is the base condition. Let's just write this base condition afterwards. First thing is we will call upon the recursive function list node star x. So we want that answer should be stored in x, that is the head that should come after this recursive call should be stored in x. So we'll say reverse and we'll pass on head connects in this, right? Now x is having the entire linked list. Like x is having what? It is having 5 4 3 2 1 with x pointing to 5. Now my task is heads next ka next should be equal to head. Like the last second step, 2 I'm pointing this 2 to 1, right? And head should point to null. This is what I want to have. And what should I return? I should return this x only, right? This x only should be returned because it is pointing to 5 and I want to have a linked list with 5 4 3 2 1. So what should be the base case? Base case will be if heads next is not equal to null, I'll simply return head. ठीक है जी. Let me just remove this iterative code from here. Here also we'll put a check. If let's say if head is equal to null initially only, then we'll simply return null, right? And else we'll return reverse of head. We'll call upon the function reverse of head. I hope this should work fine. Let's just try to run and see how it goes. Okay. There is a little bit of problem. It should not. It is equal to null. When heads next becomes equal to null, then only we were returning. Now this should be the base case, right? Okay. So there is some error. Let me just try to debug. What is the error? It should be head itself, right? Just a minute. So it should be head ka next is equal to null. This was the problem, I guess. So not to make the head equal to null, we want to make the heads next equal to null, right? What actually I'm trying to say in this case is, like, we had this 1 2 3 4 5 and null, right? This part was handled by recursion. We get the answer in x is pointing to 5 and we have this linked list 5 4 3 2, right? And null. This is the linked list that recursion gives us, and x is pointing to this 5. So now I want to point this 2 to this one. So this is the step that does that. Heads next ka next equal to head. So this is done. Now 1, this is head. Heads next should point to null. So heads next should point to null and we should return x. So this is the step that we were missing. Let me try to run it again and see how it goes. Probably it should pass. Let's see. So yeah, so it is passing. We have 1 2 3 4 5 and we have the expected output as 5 4 3 2 1. I hope this code is clear to you, and now you can successfully reverse a linked list using both iteration and recursion. If somebody asks you to what is the time complexity in both the cases, right? This is something that can be asked in our interviews. So what will be the time complexity? Time complexity in both the cases will be almost similar, right? Because we are moving at n nodes of a linked list. So it will be O of n. Space complexity in iteration case will be O of 1, right? Because we are just making 3 pointers, nothing else. But space complexity will be there in the recursive case because we create a recursive stack internally. So space complexity wise, iterative solution is a little better, right? So make sure you check with this point as well in your interviews. So the next question that we have is basically merge two sorted linked lists, right? So what is given to us in the question is, the problem statement is like this. We have a list 1. Let's say this is the linked list 1. We have list 2. We have a second linked list and both of them are sorted. This is given in the question. Let's say we take an example of 3, let's say 5 8 and null. Let's say another linked list 1 4 9 and null. So we have the situation, we have been given two linked lists, linked list 1 and linked list 2, and we need to merge both of them. That is, our answer should be something like 1 3 4 5 8 and 9 null. This is what we are looking forward to as an answer in our merge to sorted lists, right? This is the answer that we need. So how can this be done in the best possible way, right? So there are two approaches again for this particular question, and we'll discuss both of these approaches. One is a recursive approach, a pretty simple one. The second is basically an iterative approach. Firstly, I'll help you understand the recursive approach, right? So let's say we have two pointers L1 and L2 pointing to list 1 and list 2, right? So now you see in this particular given linked list, like it is a sorted list, so the smallest element will lie at this, the head of the list L1, and the smallest of the list 2 will lie at the head of list 2, right? So out of both these lists, which will be the minimum element, the smallest one, right? So how we can get that? We will get, it can be either the smallest of L1 or the smallest of L2, right? So we'll compare L1 and L2. Let's say out of L1 and L2, 1 is the smallest, right? So now I know that I have got the smallest element, that is 1, right? So I'll pick this up. So this will be my list 2. List 2 comes out to be the smallest. Like I'll compare list 1 value and list 2's value. So now list 1 value is greater than list 2. So list 2 is the smallest element, right? So list 2, I'll start from here. And the rest of the part, I will say to recursion, this is the list I am passing, this is the list I am passing. Merge both of them and give me the final answer, right? So what recursion will do? Recursion will pass this also and this also, and it will give us the final answer, that is X. So now this X will be having a merged sorted linked list containing the complete list L1 and the remaining part of L2. So our next task would be, we just need to attach list 2's next with X. So as soon as we attach this, we will say that our lists are sorted. Pretty simple, right? What all test cases, base cases we need to solve upon? Let's say we are given list 1 is equal to null. If list 1 is given equal to null, what we can do is we can simply return list 2, right? Second thing can be, if list 2 is equal to null. If list 2 is given equal to null, we can simply return list L1, right? Let's just try to code it a bit and then we'll dry run it so that you can understand it a little more better, right? So this is the problem that is given to us, that is merge to sorted lists. You are given heads of two sorted lists, list 1 and list 2. Merge the two sorted lists in one sorted list. The list should be made by splicing together the nodes of the first two lists, right? So let's say, so we are given this particular function merge to list 1 and list 2 we are given, right? Let's create our own merge function, list node star merge. In this we have list node star L1 and list node star L2, right? So the base cases were, if at all L1 is equal to null, then what we'll do, we'll simply return L2, right? And if L2 is equal to null, then what we'll do, we'll simply return L1. So these are the two things, these are the two base cases that we have, right? After that, what we are going to do is we're going to compare. If L1's value, let's say L1's value is less than L2's value, so that means the first element, the work that we are doing is on L1, that is L1 is the smallest element or the minimum of both the lists, right? So what we'll simply do, L1's next may I will put what I will get from the recursion. So what I'll put in recursion, now I know L1 is the smallest element, so instead of L1 I'll pass L1's next right? And along with that I'll pass L2, right? So now list 1, this recursive function, that is list 1 ka next and list 2, this merge function, I am expecting that it will give me the combined merged results of both of these lists, list L1's next and L2, right? After that I don't need to do anything, I just need to return this L1 and we are done. But what about the second case, right? Else part. Let me write down the else part. So what happens in the else part is I will do L2's next is equal to merge. If L1 is not smaller, then it's obvious that L2's value is smaller from both of these sorted linked lists. So I'll merge here L1 complete and L2's next. What I'll return in this case is I'll return L2. Right, so now we have L1 returned, we have L2 returned, and this function I believe is done. Let's just try to return and call this merge here. We could have done it here only, that would not have been a problem. We can do it here also. Let's just do it like this: list 1, list 2, and let's try to run the code. So we have successfully merged both of these two linked lists 1 2 4 1 3 1 3 4 as 1 1 2 3 4 4 1 1 2 3 4 4, right? So now you can see what is happening is, if L1 is equal to null, we return L2 simply. Like, let's say if list 1 is not there, then we simply return list 2. Similarly, if list 2 is not there, we simply return list 1. So both of these things are done, right? After that, the first case, we'll compare the first element of both of these: 1 2 4 1 3 and 4. We'll compare the first element of both of these. So the first element of both of these is same, so we can take any one. Let's say we take this one, right? So L1's next. So now this is what I am passing on to recursion, and I believe that recursion will give me the correct answer after merging. So what recursion gives me is 1 2 3 4 4. This is what recursion has given me, and this is stored in merge. Now what I just need to do is L1's next may I need to put this one. So I get this final answer as 1 1 2 3 4 4, right? Similarly, if we take the second case, if L2 is smaller, then we'll take this case and we simply merge. This is how recursion works here, right? If let's say we don't use recursion and I want to do it by iteration, right? So how we'll do that? Let's just discuss the approach for that as well, right? So now what we're doing here again is, so yeah, so here again, now let's just take that same example: 1 4 8 null. This is list 1, this is list 2. List 2 is 2 3 and 5 null, right? Again, what we have to do is we'll have to compare this first element of L1 and L2, L1's value and L2's value. So I'll compare both of them. If L1's value is less than L2's value, right? So in this case, I'll take a dummy node. Let's say I create a dummy node and I initialize it as -1. Also, I'll maintain a tail variable which will point to this dummy node. Let's say dummy node is answer. Let me name it as answer, and this tail is pointing to answer. Again, we'll point the same base. For here, what I will do is I'll compare L1's value with L2's value. If L1's value is less than L2's value, then I'll point tails next to L1 and I'll update my tail so as to keep a track of that how far we have gone. This tail variable is due to that, right? Tails next is equal to L1. So now this is done. What I will do is I'll move L1 here and L2 is still here. Again, these both will be compared, L1's value and L2's value, which is smaller. So now 2 is smaller. So what I will do is tails next will be equal to L2, right? Then again L2 will move, L2 will come here. Now we'll compare this L1 and L2 again. L2 will again put tails next is equal to L2. Now this is done, L2 will be here. Now we'll compare L1 and L2 again. So now 5 and 4, which is smaller? L1. So we'll put tails next is equal to L1 and we'll move L1 here. Now we'll again compare L1 and L2, which is smaller? L2 is smaller, we'll put tails next is equal to L2. Now L2 becomes null. As soon as any of these linked list becomes null, then the second linked list as such we'll have to attach in our linked list, right? 8 is left. Let's say we had 9 or we had 12 also. So now we have reached a null here. So the remaining elements of the first linked list will attach as it is, right? So I believe this also, when we'll code it right, you will be able to understand it a little more better, right? So let's try to code this as well. Let me just comment down this code. Right, so merge to sorted linked lists, merge to lists. So here also the first thing is, if at all I know that list 1 is equal to null, so what will happen is I'll simply return list 2, right? If list 2 is equal to null, I'll simply return list 1, right? I'll maintain a dummy node. Let's say list node star answer is equal to new list node, and let me just initialize it to anything we can initialize. It can be 0, it can be anything. Let's say we initialize it to something as -3, right? This is something that I have initialized. After that, I'll maintain a tail variable, list node star tail is equal to answer. So this is pointing to answer. This is just to maintain ki where we are reaching in our linked list. This is basically a tracker, you can say, right? Again, this loop I'll run until and unless either of my list 1 is complete or my list 2 is complete. Until L1 is not equal to null and L2 is not equal to null. Either of them is not equal to null. So now I'll see if L1's value is less than L2's value, right? If L1's value is less than L2's value, then what we are going to do is tail ke next mein we attached L1, right? And now tail becomes equal to L1 and L1 increases. So L1 here is like in the previous question we took it as L1 and L2. Here we are taking it as list 2 and list 1. So let me just rename it as list 2 and list 1. So tails next, it's list 1, tail is equal to list 1 and list 1 is equal to list 1's next, right? So this is the if statement, the first if statement. Else, if this is not the case, that is list 1 ka value is greater than list 2, then same thing we'll do with the list 2. Tails next is equal to list 2, tail is equal to list 2 and list 2 is equal to list 2's next, right? So this is something that we have done, and we'll have to check those two cases. If at all one linked list is complete, and then the rest of the linked list will be as such. So for that, if L1 is equal to null, then what we can do is we can use tails next is equal to L2, right? Else tail ka next will be equal to L1 to L1. Again, it's L1, L2 is list 1 and list 2. Right? After that, what we are going to return is we are going to return the next of the dummy node, right? Let me just explain it to you. Once we write the code, answers next are going to return. Let's just run this code. Okay, so it is list 2. So we've successfully submitted and the solution has been accepted. So what we are doing in this particular case is, let's just try and see again. So firstly, we are making the checks. If list 1 is null, we'll simply return list 2. If list 2 is null, we'll simply return list 1. After that, what we have done is we have created a dummy node answer, right? This is the dummy node answer, and we have made our tail pointer to point to this answer. Initially its value is -3. It does not matter. You can name give it as -1, -5, -10, anything, right? After that, we have put a check. We have two lists, list 1 and list 2, right? Let's say it is 1, 3, 5, it is 2, 4, 6, and then it is null, right? So what is happening is, until and unless list 1 is not equal to null and list 2 is not equal to null, right? So we'll perform these operations. First thing is, we'll check this. If list 1 ka value is less than list 2 ka value, that is if 1 is less than 2, yes, it is true. So what I will do is, tail ke next mein I'll put, tail ke next mein answer mein I'll put list 1, matlab I'll put 1. So this is what is happening, right? Answer ke next mein sabse pehle 1 chala gaya. After that, tail is equal to list 1. Now tail is updated here and list 1 moves forward. Now list 1 becomes here. Now again this is done. So if statement we have gone to, again we'll move into the while loop. Is list 1 null? No. List 2 null? No. We'll again compare L1 and L2. Which is smaller, 2 or 3? 2 is smaller. So what we'll do is, now 2 is smaller, right? So we'll not go in the if part, we'll go in the else part. So tails next is equal to list 2. So tails next is equal to list 2, that is 2 will attach here. Now tail is increased to here and list 2 becomes here. Now again we'll compare L1 and L2, which is smaller, 3 or 4? 3 is smaller. What we'll do, tails next is equal to list 1, so it will become 3. Tail is equal to list 1, so tail becomes list 1, tail is here, and list 1 is equal to list 1 connects. We'll move L1 here. We'll again compare this 4 and 5 and so on. We'll go till the end and we'll have a sorted linked list 1, 2, 3, 4, 5 and 6. So this completes this particular line of codes, right? So after this, let's say why these two lines are there. Let's say I have this linked list 1, 2, sorry, I have something of this particular sort: 1, 3, 5, 7, 9 and null, and second linked list is 2 and 4 null, right? We compare this and this, we attach 1, 2, then we attach 3, then we attach 4. Now after 4, this has become null. As soon as list 1 becomes null or list 2 becomes null, so is it that I'll stop doing anything? No. What I will do is, after 1, 2, 3, 4, I'll put all the elements 5, 7, 9 in the complete list. This is what I'm doing in these two steps, right? So at the end, what we are doing is we are returning answers next. That is, initially answer was -3. -3 के next से ही हमारी linked list was starting, and that is what we are returning. I hope this is clear, right? So we have successfully solved this problem using recursive approach also and using iterative approach also. Now let's see another problem. So the next thing that we're going to see in this particular video is the question. It's also an easy problem: remove duplicates from a sorted list, right? You're given the head of a sorted linked list and you need to delete all the duplicates such that each element appears only once, and you need to return the linked list sorted as well, right? So this is the linked list that you have: 1, 2, 2, 3, 3. This is the sorted linked list that is given, and you need to return a linked list by removing all the duplicates. 1 is occurring 2 times, so we need to remove this for once. 2 is occurring 1 time, that's fine. 3 is occurring 2 times, we need to remove 1, so we need to return 1, 2, 3. This is the problem statement, right? Now let's discuss the approach, how we can solve this particular problem. So remove duplicates. Right, so this is the problem statement that is given to us. So let's say this is the example: 1, 1, 2, 3, 3 and null. So again, for solving this particular problem, I have two approaches. One is recursive and one is iterative. Let's first understand the recursive approach, then we'll go on to the iterative approach and we'll see how we can solve it in the best possible way. So this is the list that is given to you and you need to remove all the duplicates. What happens in recursion is we take a small part and we tell recursion to solve the larger part for us, right? So we break this linked list here, we pass this entire thing to our recursion, and I believe that recursion will return me the list after removing all the duplicates. That is, recursion will return me 1, 2 and 3. Right, so this is the result after I pass on to the recursive function. So now the next thing that is my turn, what I need to do is I need to check this head and the first element of the recursive result. So if they are same, that means one is here also, one is here also, so I need to remove this. So I'll simply return my recursive head. Else if they both are different, right, this head is different and recursive head is different, so I'll have to attach this recursive head to heads next. So heads next will be equal to my recursive head and I'll return this head in that case, right? You will be able to understand it better when we'll code it. So let's just move up onto the IDE and try to code it, right? So we are given the head of the linked list. So the first thing, that is the basic thing, that what we need to check is we need to check if head is equal to null or heads next is equal to null. If both of them, that means it's just one number, so it can't be duplicate, so we need to simply return head in this case, right? Next thing is I'll call upon recursion list node star x. So I will store the answer of that recursion in x. So what I will do is I'll call delete duplicates heads next, right? So the entire result after recursion will be stored in this x, right? Now I need to check if the heads value is equal to the value of x. If this is the case, then what is the next step? We'll simply skip the head and we'll return x as such, right? Else what we'll do, else I will attach the heads next to x and will return this head. I hope this is clear to you. There's nothing very difficult to understand. So what we are doing in this particular case is, let's say we have this example 1 1 2 3 3 and null, right? So initially we are checking if head is equal to null or heads next is equal to null. So we have checked both of them, they are not equal to null, else we would have returned head simply, right? Next we are calling upon recursion for this part, we are passing upon heads next and we are expecting the answer in x. So what will x have? X after recursion will have 1 2 and 3 and null. Now next case is I'll compare if the value of head is equal to value of x, that is this value, if it is equal to this value. Yes, this is true in our case, so we'll simply return x. So we'll simply return this x as my answer. Else if they both would not have been same, then what, let's say it would have been 0, then I'll compare 0 and 1. Else part will go on, we'll put on heads next as x, matlab 0 ka next I'll put this x and I'll return this head. So now my answer would be in that case 0 1 2 3, right? I hope this is also clear, right? Now let's discuss the iterative approach on how we can solve this particular problem. Just think upon how the iterative approach would be, right? So how the iterative approach would be, so let's say we have this 1 1 2 3 3 and null, right? So in the iterative approach also, these two, this step is going to remain the same. We'll check for if head is equal to null or heads next is equal to null. We'll simply return head. What will change in iterative approaches, we'll run a while condition until and unless this head is not equal to null. What we'll do is we'll simply compare the data of head with heads next, right? We'll compare the value of head if it is equal to head के next की value, right? If both of these values are same, so what I need to do is I need to simply skip this part, right? So for skipping this part, what I need to do is I need to make this connection. So for making this connection, I need to have the address of this. Let's store the address of this in a variable a. List star a will be equal to temp ke next ka next. So temp is this, temp or head you can say. Head ke next ka next, head is this, head ka next is this, next ka next is this. So we stored the address in a variable. Next, what thing I'm going to do is temp ka next I'm going to make it as a. That is iska next I'm going to make it as a, and this will be removed. Else what I'll do, if this is not the case, like both of them are different, 2 and 3 are different, so what I will do is I'll simply move temp to temps next. So this is going to be the code for this particular question. Let's just try to see the approach. Let's just try to see the code so that you can understand it in a more better way, right? So what happens in the code part is this head is equal to null or head connects is equal to null remains the same. Again, let me just remove this code part. So instead of using head, I'll create a temporary variable list node star temp is equal to head. Fine. So what I am going to do after this, so after this I'll check for I'll put a while loop, right? While temps next is not equal to null. So we'll check for if temp ka value is equal to temp ke next ka value, right? So that means both are same, so we need to skip that number. How we were skipping that number was list node star a is equal to temp ke next ka next, right? And we were simply putting temp ka next is equal to a. That is, we have skipped the middle node directly. Else part mein I was simply moving temp is equal to temp ka next, right? Let me just try and run this as well. Okay, there's one extra bracket. There's some problem with the brackets. Let me just check, right? This is for this is for this is for this. There's no problem with the brackets. Let's just try and run this again. Oh, so we haven't returned anything in this case. Okay. Sorry. Yeah. So we are to return head itself. Yeah, so we have finally got the answer. This is correct answer 112. The list with all the duplicates removed is 12, and let's just submit this and see how it goes. So we successfully submitted this as well. So now I hope you have understood the recursive as well as the iterative solution of remove duplicates from a sorted list. This can also be asked in your interviews. So now let's move up on to the next problem. In this video, we are basically going to discuss a new problem, that is add new two numbers. So what you're given is you are given two non-empty linked lists representing two non-negative integers. So this is the condition that is given. The digits are stored in reverse order. Basically, the digits that you are given, they are stored in reverse order. Each of their nodes contain a single digit. Add the two numbers and return the same sum as linked list. So you will be given two heads of two linked lists, and they will be representing two numbers present in reverse order, and you need to add these two numbers. You need to add these two individual elements of linked list separately, and then you need to return the answer in the form of head of the linked list only, right? So let's see with this with an example, and then we'll try to see how we can code this better, right? So let's take an example where we have something of the sort. Let's say we have 4. Let's say we have 4, we have 6, we have 2, and we have null. Second, like we have this linked list L1, we have this linked list L2. In this we have 2, let's say we have 8, we have again 8, and let's say we have 1. So we are given this L1 and L2 that points to the head of linked list L1, L2 points to the head of linked list L2, and we need to return our result. So the result would be in such a way that these numbers are given to us in the reverse order as per the mentioned. So the original numbers will be 264 and 1882. So when I add these two numbers, so it will be 4 plus 2 6, it will be 8 plus 6 14. So 4 will be here and 1 will be given as carry. So 8 9 10 and 1 11, 1 and 1 will be again carry. 1 and 1 when added will give us 2. So the answer is going to be 2146. So we need to return, let's say we need to return result, and the result should look something like 6 4 1 and 2. So this is something that I want to return. I want to point this result to this head of the answer, and I need to return this result. So this is something that we're looking forward to in this particular question. So for solving this question, let me take a dummy node. Let's say I'm taking a dummy node D. So this is the dummy node, and let's start pointing it to let me just take this as L1, this as L2. We'll take two variables, sum and carry, right? So we'll try to add individual L1 and L2. We'll first of all I'll go and check if L1 is empty or L1 has something. So if L1 is not empty, I'll go to L1 and I'll add L1 and L2 together. So when I'll add L1 and L2, I'll put that thing in the sum. So 4 plus 2 comes out to be 6. So I'll have 6 in the sum, and also I'll make a new node with 6, that is sum. I'll insert into this list and I'll point this to this, let's say it's pointing to temp, and I'll point this dummy node to 6. Now temp will move on to this 6. As of now, this is what is happening till now, right? And carry is 0 in this case, right? So what we're going to see in the next, like we'll move L1 one step forward, we'll move L2 one step forward. Now again we'll once 6 is written here, we'll remove 6 from here, and it again turns out to be 0. So now we'll add 8 plus 6. We'll check if L1 is empty or L2 is empty. As soon as any one of them is empty, will not do anything, but they are not empty, so we'll add 8 and 6. Adding 8 and 6 will give us 14, so we'll put 14 in the sum, right? And we'll create a new node, and inside this new node, what we'll put, we will be putting sum modulo 14. This is something that we'll put in sum modulo 10. So what is the sum now? It's 14 modulo 10, that is 4. So we're going to put 4 in our new node, and we'll point this temp to this. And inside our carry, what we are going to put inside our carry, we are going to put 14 divided by 10. So when I say 14 divided by 10, it gives out to be 1. So my carry becomes 1 now, right? So now again 14 is gone and 14 turns out to be 0, right, with carry 1. So now this carry is also there, right? Now this carry is also there. So what happens is, as soon as I move L1 to here, L2 to here, now while calculating sum, I'll add this carry also, right? Once I'll add this carry, so it becomes 8 plus 2 plus 1, so it is 11. So 11 is there in the sum, carry becomes 0. Now what I'll be putting in the next node? In the next node, I'll be putting sum modulo 10, right? So that is 11 modulo 10, that gives 1. So I'll be putting 1 here. And in the carry, what we'll put? Again 11 divided by 10. So 11 divided by 10 is again 1. So I'll put 1 in the carry again, right? As soon as this is done, so we'll put sum is equal to 0 again, and we'll move L1 and L2 further. Now L1 is not there, right? So we'll not take L1 now, but L2 is there, and along with that a carry is there. So carry is 1, L2 is 1. When I'll add L2 and L1, when I'll add L2 and carry, so it comes out to be 2. So I'll have 2 in the sum. So what will be there in the carry? That is 2 divided by 10. 2 divided by 10 and 2 modulo 10. 2 modulo 10. So 2 modulo 10 will give me 2 again. So I'll add 2. I'll move the temp here. Earlier also I'll move the temp here, and 2 will be pointing to 2. I'll create a new node and I'll add 2 into it. 2 divided by 10 gives me 0. So I'll make carry equal to 0. So in this way, now my L1 is also empty. Now like till how long I'll have to run this loop? Either we'll check for L1 whether it's empty or not, we'll check for L2 whether it's empty or not, and also we'll check for carry if it is empty or not. If there is only carry left, then also we'll add only carry to our new we'll make a new node and we'll put that carry into our new node and we'll point that to null. So that is basically what we are trying to do in this particular question. We'll point this to null at the end and we'll return the dummies next. Dummy ka next is basically the head of our new answer, so we'll return dummies next as the output. So this is going to be the approach. Talking about the time complexity, so it will be O of m or n, the length of the longer linked list, right? If it's L1 or L2, so it's basically the time complexity goes according to that. Also let's now discuss the code part. Like if you are trying to code this particular solution, then how this is going to actually work and what all things we need to do. Basically we will be doing the same what I have explained to you here in the explanation part. Right now let's move up on to the code part and see how we can code this. So basically what we are given L1 and L2. So L1 and L2 points to the head of two linked lists L1 and L2. So firstly I'll create a dummy node as per I have explained you. It's list node. Dummy is equal to new list node. Then what I'll do, I'll create a temp variable that is pointing to this dummy. So this temp will be taking forward when we add a new node to our result dummy linked list, right? So temp will point to dummy. After that we'll initialize a carry variable which is equal to 0, right? So we'll run this while loop until and unless we discuss about three conditions. Firstly, L1 should not be equal to null, or L2 should not be equal to null, or carry should not be equal to null. So these three conditions these should satisfy until and unless this loop will run, right? So int sum is equal to 0. Initially I have initialized the sum is equal to 0. Its value will be what we'll be going to see from L1 plus L2 plus carry, right? We are going to do this. So inside this we'll check two other conditions. If L1 is not equal to null, until and unless L1 is not equal to null, what we'll do, we'll add the value of L1 in sum is equal to L1's value, right? And then we'll move on L1 further. L1 is equal to L1's next, right? Again, if L2 is not equal to null, then what we'll do, we'll do sum plus equals to L2's value, right? And we'll do L2 is equal to L2's next, right? So we have done these two things. After that what I was doing is I was adding the value of carry in sum. That's the third thing, right? And what was the value of carry? Carry was equal to sum divided by 10. What after this, we were creating a new node, list node, in which we are storing the answer. Node is equal to new list node, And what will this list node have? List node will be having sum modulo 10, right? Why this sum modulo 10? Because like we saw that the last part was like, let's say we have 14 as the sum, so 4 will be there in the list node and 1 will be given to the carry. So we have given carry as sum divided by 10 and the number in the list as sum modulo 10. Next thing is, we'll be moving apart our temps next is equal to this node that we have created, and then we'll move on temp further. Temp is equal to temps next, right? At the end, what will return? Will return dummies next, and we are done. This is basically what we have done and what we have understood in that particular solution. Let's try to run this code and see if it is working. So we were to create list node here. I think everything else should be fine, or if there is some typo. Okay, so it's val, not value. Okay, so for this particular case, like 2, 4, 3, 5, 6, 4, we should have 5 plus 2, 7, 6 plus 4, 10, 0, 1 is carry, 4, 5, 6, 7, and 8 should be the answer. 8708 is what we are getting as the reverse number. So exact answer should be 807, but we need to return the reverse, so it is 708. Hi. So the next question that we have, right, so the next question that we're going to discuss is basically to detect a cycle in a linked list, right? We have discussed some of the problems in linked list. Now it's also a very, very important problem from the point of view of interviews. So linked list cycle detection, right? So what exactly does this mean? Let's say you know what is the structure of a linked list, right? We have something known as nodes, in which first node is connected to the second node is connected to the third node is connected to the fourth node, and fifth node, let's say this is connected to null. This is a kind of a linked list that you are aware of. We have something known as head, where we can access the complete linked list, right? But let's say you have an example in which you have linked list of this particular form: 1, 3, right? Or it can be 1, 3. It can be of this form. So now what happens in this linked list is there's no null, right? You don't find any null here. Or it can be something like this also, right? So now you move from 1 to 2, 2 to 3, 3 to 4, 4 to again 2, 2 to 3, 3 to 4, 4 to again 2, and this continues forever. This is a linked list with a loop, or a linked list with a cycle. So here this cycle exists, right? Similarly here also, you start from 1, you go to 2, you then go to 3, and again go to 2, go to 3, again go to 2, again go to 3, 3 2 3 2 3 2 3, and it again forms a cycle. So what we are supposed to do in this particular problem is we need to detect these cycles, right? So when I say detect these cycles, so from the point of view of cycle detection, you need to tell, you need to return a true or a false to confirm whether a cycle exists or not. And if it exists, you have to return which is the first node where it meets, right? You'll have to tell which is the first node where it meets. So this is basic cycle detection part. So what can be the approach, how we can solve this particular problem, or how we can approach to this particular problem? There can be various methods, right? So the first and the most important thing that comes to our mind is, let's say I have something of this sort: 1 2 3 4 5, and we have this particular cycle, right? So we have nodes like 1, 2, 3, 4, and 5, and 4 traces back to 2, then 2 to 3, 3 to 4, and it's in this fashion, right? So what can be done? So the first thing that comes to my mind is, let's say I create a hash map. So hash map is a data structure in which I put all the nodes along with their frequencies, right? Let's say 1 is there, 1, and I put its frequency as 1 again. uh, or you can say, like, I have uh, uh, a hash map, like let's say 1, then 2 with an entry 1, then 3 with an entry 1, 4 with an entry 1. As soon as it moves from 4 to 2 again, so I can see 1 is already present in the 2's column. That means 2 already exists in this linked list. So as soon as this conditions occur, what we can say is that this linked list contains a loop or contains a cycle, right? This part is done. Now, at which node the cycle exists? So the cycle exists at this node 2. So the first number that exists more than once is the node where the cycle exists, right? So this can be one simple approach that we can follow for solving this particular problem, right? But what is the problem in this particular approach? When I say problem, so there can be a problem with respect to this hash map. So to create a hash map, we need space, right? So this accounts for a time for a space complexity of O of n. So I have this extra space complexity, so I need to reduce this at any cost, right? So this is a very I would say lovely method that we have already used when we are finding the middle of the linked list, right? We found the middle of the linked list by some method. I'll just make you revise that as well. But for discussing this problem, we are discussing a very important algorithm that is known as Floyd Warshall cycle detection algorithm. So what happens in this particular algorithm is, and it's very magical. Look, you will love this way that we solve this particular problem, right? So how we are going to do this actually? Let's say you have this linked list 1, 2, 3, 4, 5, and 5 traces back to 2, right? So what you are going to do in this case is, you take two pointers. कौन से pointers? You take two pointers, slow pointer and fast pointer. So both slow pointer and fast pointer are initially at this point, right? Slow pointer is also here, fast pointer is also here. Both slow and fast pointer are pointing to this. Now make the slow pointer point a move one step at a time. Make the fast pointer move two steps at a time, right? So what I'm trying to say in this particular thing is, like, let's say if slow is moving here, fast will move here. This slow is here, fast will move here at the same point. Then both fast and slow will be cut. Slow will be here, then fast will be here. Slow will be here, then fast will be here. Then slow will be here and fast will be here. So this is a point where both slow and fast meet. So this thing suggests that cycle exists. So at any point in a linked list, if at all I find that slow and fast pointers, this is logically correct also, right? Pointers meet. At any point where slow and fast pointers meet with each other, that is the point where we can say that cycle exists in a linked list, because that thing is something that is occurring twice, right? This tells us that that thing is occurring twice. And let's take it as let's just take one more example. So let's say you have this kind of a situation in which it is 1, 2, 3, 4, 5, 6, 7, and back to 3. So like let's say this is the linked list that is given to you, right? And you have your slow and fast pointers here, right? Now you know that slow moves by one step at a time, fast moves two steps at a time, right? This is something that you know. So now slow moves here, fast moves here. Then if slow moves here, then fast moves here. 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 Now this is the point where both slow is equal to fast, right? So this suggests that cycle exists in the linked list. So this is the point that cycle exists in the linked list. And how to detect that first node? तो फर्स्ट नोड कैसे डिटेक्ट कर सकते हैं, हाउ वी कैन डिटेक्ट दैट फर्स्ट नोड? सो द पॉइंट वेयर बोथ ऑफ दीज नोड्स मीट, keep your slow pointer there and make a new pointer start which should point at the first. Now move start by one step and slow by one step. One step start moves from here to here, slow moves from here to here, start moves from here to here, slow moves from here to here. So they will ultimately meet at the first node. मतलब यहाँ से if you'll start, मतलब the point where both of these meet, यहाँ से इतना distance will be equal to this distance. थोड़ा अजीब लग रहा होगा ना, I think you might not have understood. इसका proof देखते हैं, right? Why I'm saying all this? What is the logic behind this? So what I'm saying is, let's say if we have something of this particular sort, let's say this is the cycle that is existing. This is a certain distance a that I am traveling, and this is the point, let's say, where both slow and fast pointer are meeting, right? So let me just name this point as p, right? So let's say this is the starting of the linked list. This is the pointer p, this is the distance b, and this is the distance c. So we have three different distances a, b, and c, right? And what we want to see is, like, this is the point where both of them meet, and I am saying that if we start a pointer from this p and you start a pointer from this start, both of them will meet at the starting node, right? So let's see what the proof looks like and how, why I'm claiming all this, right? So now this let's calculate the distance that is traveled by the slow pointer and the distance that is traveled by the fast pointer. Obviously the distance that is traveled by the slow pointer into 2 will be equal to what is the distance traveled by fast pointer. This is by logic, because slow is moving at single pace, fast is moving at double pace. Let's say what is the distance that slow travels. So slow pointer travels this a distance, then let's say it covers some rounds of this circle and it covers this distance b again, and it meets fast pointer here, right? So what I will write this as will be a plus b plus c, that means complete circle. Let's say it covers some m number of rounds, plus this b again, right, into 2 will be equal to fast. How many rounds will fast take? It will take a plus uh, b plus c, that is the number of rounds, into n is the, let's say fast pointer takes n different rounds, plus b again, right? Am I clear? So now this is the equation that we have. Let's just try to solve this particular equation and see what are the results that we are getting, right? So it will be 2a plus it will be 2m b plus c plus 2b is equal to a plus n into b plus c plus b, right? So if at all I solve this, I will get this. A is cut with A, B is cut with B. I'll get something like A plus B is equal to n minus m times B plus C, n minus 2m times B plus C. So this is again a constant, because let's say A takes n number of rounds, B takes m number of rounds, so this overall terms comes out to be a constant. So let's say A plus B will be equal to lambda times B plus C. This is the relation we have. Let's try for different values of lambda. Lambda equal to 1 and lambda equal to 2. Right? Now let's say I have lambda equal to 1. So what will be the case? If lambda is equal to 1, so this becomes A plus B is equal to B plus C. That means A is equal to C. So what were A and C? We had something like this. We had a point K. This was A. This is B. And this is C. Right? Right? I hope this is fine. So now A is equal to C. That means this distance is equal to this distance, is what I was saying. But you will say, sir, you have taken lambda equal to 1. Now let's say I take lambda equal to 2. What will happen? It will become something like A plus B is equal to 2 times B plus C. Is it? It will become A equals to B plus C plus C. So this B plus C is the repetition, right? B plus C is the circle repetition. So no matter how many times the circle repeats from here to here, so this will again be of no value. मतलब circle तो कितनी बार भी वो कर सकता है ना, मतलब it can do infinite number of times. So I'll neglect this circle also, right? Because at the end goal यहाँ से यहाँ तक he has to reach, यहाँ से यहाँ तक he has to reach. So this A will become equal to C ultimately. So A will be equal to C in any case, right? So this is what we have proved. Let's just dig into the code part and then we'll move on to how we are coding. जिसमें हम basically करके आ रहे होंगे detect cycle, right? What we will be given list node star head and हमें cycle detect करना है, right? So the first thing that I did was I took a slow pointer equals to head. I took a fast pointer equals to head. Then I took a what I say while loop. While this fast is not equal to null and fast ka next is not equal to null, what I do is I move the slow by one step ahead. Slow is equal to slow ka next and fast equals to fast ke next ka next, right? At any point if slow becomes equal to fast, that means they are meeting at some point. So what we did in that case, we returned true. That means cycle exists in my linked list. Else when we come out of this loop, I'll return false. That means there is no cycle in the linked list. Linked list में कोई cycle नहीं है, right? How will detect the first node where both of where the loop starts? Detect the first node where the loop starts. Now you have the proof, right? Proof of where the loop starts is, if this is the case, this is some point P, this is some point A, sorry, this is the distance A, this is the distance B, this is the distance C, right? So now you know that once you get this point, that is the midpoint, right? In here, in case of true, let's say I return the original value. Instead of true, I return slow, and at the last I return null. मतलब the point I am returning कि यहाँ पे they both are meeting. So now for detecting the first loop, what I need is I need to have a pointer that starts from the start. Let's say I have one start pointer and I should have a pointer from this mid. That is the mid pointer. How I can get this mid? I'll simply pass my head to this function that we have made above. So I have start, I have mid. Now I'll move both start and mid by one point, and the point where start becomes equal to mid is the point that is the starting of the loop, right? Now let's just try to code. Well, this is something that I believe you would have understood. If you still have doubts, make sure you watch this video again. It will clear a lot of your doubts. Now, this is the problem that is there in front of us, linked list cycle. So you'll have to return key whether this linked list contains a cycle or not. So the first step that we did was list node star slow pointer, it's pointing to head. List node star fast pointer, it is also pointing to head, right? So these two things we have. While fast is not equal to null and fast ka next is not equal to null. Now I have two things. What I will do is I'll move slow equals to slow ka next and fast equals to fast ke next ka next, right? Now if at any point slow becomes equal to fast, what I will do is I will return true. Once I come out of this loop, I'll return false. So this was the basic code behind this particular linked list function. Similarly, we can implement a little bit of change in the second part that we discussed, and we can submit this problem. We are returning a true, so this contains a cycle. Yes, that's true. So that was it for this particular video. Let's move on to another problem. Right? So the next question that we are going to discuss in the series of linked list is to remove linked list elements. Right, so you'll have to remove linked list elements. What I mean to say by this is, let's say you have this kind of a linked list in which the nodes are connected 1 3 6 2 6 4 8 and null, right? Let's say you have this linked list and you are given a value, let's say 6. You need to remove 6 from this linked list entirely, and you need to have a resultant linked list of this form. Your output that is expected should be of the sort of 1 3 2 4 8 and null. So this is the output that is expected, right? So you will have to remove the 6, you will have to remove the 6. So how can we do that? Maybe we can directly connect this particular node to this particular node. That's one thing. We can connect this particular node to this particular node. So we need to move to a node that is behind that particular node, right? So after removing this node, what we'll have is 1 is connected to 3, then 6 is removed, 3 is connected to 2, now 6 is removed, 2 is connected to 4, 4 is connected to 8 and null. So we get something of this particular sort, right? So how we can change or how we can do this? Maybe there can be some more cases. Let's say if 6 is present at the first place, right? Like the linked list is something like 6 3 6 2 6 4 8 and null. So what you will do in this case, you don't have anything behind this, so it will again be a problem. Should we handle this case separately, or rather than handling the case separately, what we generally prefer to do in questions related to linked list is we create something known as a dummy node, right? So how this dummy node will help, we'll try to see it in this particular question, right? So let's say I create a dummy node. This is dummy node D. Let's say its value is -1. Dummy node with a value -1, right? And I connect it with the head. So it will be 2 -1 6 3 6 2 6 4 8 and null, right? I create this dummy node and I attach it with my head, right? So now what I will be doing is I need to ignore this, or I need to remove this. What can be done in this case is I'll directly connect the next value of this to 3. I'll directly connect the next value of this to 2. I'll directly connect the next value of this to 4, right? So this is what I'm currently looking forward to do in this particular question. So this is the same question that is available on lead code. Let's just go to the question and see what is the possibility, right? So the question states that you need to remove linked list. It's an easy marked problem, similar to what we have discussed. They have given an example. You need to remove 6 from the linked list, right? So you are given this function, you are given the head of the linked list, you are given the value that you need to remove. So the first thing that we did in this particular question is to check the base case. If at all, let's say the head is equal to null. So what we'll do is we'll simply return null, right? This is one thing. After that, the second thing is we created a new dummy node, list node star dummy is equal to new list node, and we initialize it with -1, right? So we have created this dummy node and we connect this dummy node to the dummy nodes next to the head of our original linked list. That is dummy ka next is equal to head of my original linked list. So I know my linked list has a new node that is dummy and it is attached at the front of my linked list, right? I also create a new node by the name of list node star tail, right? And I initialize this tail to dummy. So now I'll iterate over this linked list using this tail pointer. I'll move tail one step ahead every time and we'll continue this loop until we traverse the entire linked list. So while tail is not equal to null and tail ka next is not equal to null, right? So this is the format that like for used for traversing, because we'll traverse until and unless this tail is not equal to null or tail ka next is not equal to null. What we'll check is if tail's next key value is equal to the given value. If this becomes equal to 6, let's say in this case, so what are the steps that we are going to do? We'll create a new node, list node star temp, to store the address of tail ka next. Then what we'll do is we'll change tail ka next to tail ke next ka next, tail ke next ka next. What does this means, right? So tail ke next ka next means ki this, let's say if I have tail ke next ki value equal to 6, so tail, let's say this 2, it comes upon to 2, so 2 k next, that is 6 key value is equal to value. Yes, this is true. So what I will do is I'll create a temporary variable temp which will store the value of tail ka next. It will store the value of this temp, right? And what I will do is tail ke next mein I'll put tail ke next ka next. So this is what I'm going to put. This is the connection that I'm going to make between 2 and 3, right? So this is the case, and after that what I will do is I'll explicitly delete, because they have been created dynamically. So I'll delete temp, and that's it, I guess. I'll create an else case. If the value doesn't matches, what we'll do, we'll simply move tail is equal to tail ka next. Bus. This is what is expected out of this particular question. And at the end, what we are going to return is we are going to return dummy ka next, right? Because our head starts from after dummy. Dummy is the node that we provided. So this is the case. This is the question that we have done, right? So we are getting the correct answer. Let me just try and submit. So we'll be able to submit this problem, and I hope this is clear. Also, there's one more solution to this. We can do this using recursion as well. Recursion can help us solve this problem in a much I would say in a cleaner fashion, not if not help us in reducing the complexity or so, but it will help us in solving it in a cleaner manner, right? So what exactly I am looking forward to if I'm saying recursion is, let's say what I'm saying. So now let's say we again have this linked list 1, let's say I have 6, I have 3, 2, 6, null again, right? So what I will do is, what happens in recursion? We solve a smaller problem, we break the problem and we solve a smaller part, and we want recursion to solve a bigger part, right? So we'll break the problem from here. Now this part of the problem will be solved by recursion, and I will do a small part. I'll check for this particular node whether this is equal to value or not. If it is equal to value, then I'll simply return this what I have got from recursion. Else I'll add this head and I'll return, right? So what the code will generally look like, the base condition will be same. So first thing is I will recursively call and I'll pass head ka next along with value. So this I believe will give me this as the answer: 3, 2 and null. So this is the answer that I'll get from recursion, and then I'll put a check on my head. If the value of head is equal to value, that means if it is equal to 6, then what I will do, then I'll simply return this. Else what I will do is I'll attach head ka next, and head ka next equal to the recursive answer, and I'll return this head. So this is the question, this is the approach that can be followed if you are keen on using recursion here. Let me just clean this code and see this upper line will be the same. If head is equal to null, we need to return null in this case also. So this serves as the base case for this particular question, right? And yeah, so what I would be doing is I will create head ka next is equal to, I'll recursively call remove elements, I'll pass head ka next, and I will pass this value. So now I have a linked list in which head is not checked, but rest of the linked list is checked whether it contains the same element or value, element with the same value or not. Right now I'll need to check with my head. If at all head ka value is equal to my original value, then what I'll do is I'll create a list node star answer is equal to head ka next, right? And I will delete this head explicitly. Maybe I'll return the answer, right? In this case, if the value is equal to same, so I simply return head ka next. This step I am doing just because I need to explicitly delete. We can skip this step also, it will not create much difference, but we should be completely correct. Else we'll simply return head. This is the case. Let me just try and submit this as well. Yeah, so this is also getting submitted. I hope this is clear to you now. Now let's see how we can solve the next problem. So now let's read another question. In this question, they are asking us to design browser history, right? How our browser history is made and how it is used in a particular browser, let's say in Google Chrome, right? So what they want us to do is, you have a browser of one tab where you start on the home page and you can visit another URL, get back in the history number of steps, or move forward in the history number of steps. Implement the browser history class, right? We need to implement the browser history class. So browser history class initializes the object with the home page of the browser, correct? Visit URL from the current page, it clears up all the forward history. Back, move steps back in the history if you can only return x steps in the history, and if steps are greater than x, then you will return only x steps. You return the current URL after moving back in the history, and similarly you'll have to create string forward. So what they're trying to say in this particular question is, I'll try to make this statement pretty simple for you, right? So what they want us to do in this particular question is, they want us to design browser history, right? Browser history is how our browser actually work. Let's say you all might have used Google Chrome, or you might have used Mozilla Firefox, right? So let's say we are on first site. Let's say I have opened my LinkedIn. Then from my LinkedIn, I move on to another site, that is Lead Code. type in the URL of lead code and I land it on lead code. Then from lead code, let's say I want to go to interview bit, and from interview bit, let's say I want to go to Instagram. So these are the 4 sites that I'm visiting from my browser. First, I was on LinkedIn. I typed the URL lead code. I was on lead code. I typed the URL interview bit. I was on interview bit. I typed the URL Instagram. I am on Instagram. Now using the back functionality, there's a back button on our browser. Using the back button, I can move from Instagram to interview bit. I can move from interview bit to lead code. I can move from lead code to LinkedIn. Right? Again, let's say I'm like I haven't like again I want to move to lead code. So again I'll do the next, I'll move a step forward and I'll go to lead code. Now let's say I am on lead code, and in between there I felt that there's a very important mail that I have got. So I want to go from lead code to Gmail, right? I want to go from lead code to Gmail, and I'll put the URL of Gmail on the same lead code page. Then I'll move on to Gmail. And now once Gmail is opened, this entire history is lost. This is lost. Now I have this chain formed. The new chain that is formed is LinkedIn, lead code, and Gmail. Right, so this is the new chain formed. So how can we implement this functionality particularly in our code? So this is what they want us to implement. Firstly, like once we open any browser page, once we open LinkedIn, we need to initialize that page. First thing. Secondly, we want to move from one site to another. Let's say I want to move from lead code to Gmail. So this entire thing is to be deleted. That is after lead code. So visit function I need to create. Third function that I need to create is back function if I want to move from interview bit to lead code or lead code to LinkedIn. Fourth thing is forward function if I want to move from LinkedIn to lead code or lead code to interview bit or interview bit to Instagram. So this is the functionality that I need to implement, and as you can see, we are going backward and forth at the same time, right? We are moving ahead also, we are moving back also. So which data structure provides us this functionality? Isn't it a doubly linked list? Doubly linked list is of this form only now. We can move back also, we can move front also. It has 2 pointers, previous and next, previous and next, previous and next for each node, right? It is of this particular format. It's of this particular format. So I will create a doubly linked list. Right? So using this doubly linked list, what I will be doing is I will be implementing this functionality, right? So I'll quickly take you to the code, but before that I was just want to remind you one thing. Like we have already discussed STL, right? In STL, how we used to write a doubly linked list, we used to write it by the name of list, and here the type of list, like what type of elements I want to insert in that list. So I'll create list using STL, and we will try to solve this problem, right? So now this is the problem that I have in hand. So I need to first these are the 4 functions that I need to implement. First is browser history. I have been given a home page, I just need to open that home page, that is I want to start, right? And next I need to visit a particular URL and remove all the URLs or all the pages that are in front of that. If I want to move from one node to the previous node, or if I want to move from first node to the like forward button and backward button, that I need to implement, right? So the first thing is I'll create a list, and the type of list will be string because will be passing URLs. So list string. What is the name of this list? Let me name it as browser page, right? I'll also create an iterator that will help us iterate over these pages. So how we generally create an iterator? List of string, let's say it iterator it. So this is how we have initialized our iterator. Now the first page is browser history. So this is the first page and they have given us this home page. Now I simply need to push this home page in my browser page, right? So for this, what I will do is browser page dot push back home page, right? And I will make my iterator point to homepage dot begin, right? So this is, sorry, it's not homepage, it's browser page. Sorry, homepage is so something that we've added. It will be browser page dot begin, right? So this is done, I guess. Like we just need to push that particular homepage in our browser page. That's it. Now if I need to visit a new URL from the middle, right, what I will do is I'll delete all the nodes which are next to that particular URL where we are currently are, right? So how to find where we are currently are? We'll find it using the iterator, because that iterator will point to the current page, right? So let me just name it as auto current is equal to it. So this will give me the current page iterator. What I will do is I will increase this iterator, sorry, current plus plus, right? After that, what I will do is from this browser page I will erase all the elements starting from this current to browser page dot end, right? After this is done, now the new URL that I have, I want to visit that. Simply I'll push back in my browser page, browser page dot push back, and what I will push back is URL, and I will do it plus plus. So this is the visit function we have created. Now back function, if I want to go to the previous pages using the bag functionality, right? So what I will do is and they have given us how many steps you need to move back. So until these steps are decreasing, we'll simply use a while loop. While steps minus minus, what I can do is I will do it minus minus, that is my iterator is pointing one step behind, and I'll simply return star it. That means I am returning that particular string, right? But I think this is not sufficient. Like at a certain point we need to stop, right, when we are at the first page, because before the first page there is null, after the last page there is again null. So we need to stop at some point. So for that stopping condition I need to put one more condition, and it is not equal to browser page dot begin, right? So this is the back functionality implemented. So what we'll be doing in front functionality is the code is going to be almost similar, just we need to move it forward. So I'll do steps minus until steps are decreasing, how many steps we need to move forward, right, until this it dot end is equal to browser page dot begin की जगह पे end आ जाएगा, right? And this end will be browser page dot end. This is the internal functionality. This will give us the page which is after the end browser page. So we need to be at a position which is the last browser page. So last browser page I'll get it by using minus minus of end, browser page dot end, right? Simply here also we'll return and here we are increasing rather than decreasing. I'll return star it, and this is it. I hope this is clear now. Let me just take you through how we have implemented this. Okay, so now if you see, so we have been given this browser history function to be completed, and we are given this home page. So what we are simply doing is inside this list initially, which is empty, which is null, I am adding this first home page, and I'm pointing my iterator to the starting of this particular browser history, browser page, linked list, right? Then they have given us a function to complete, that is visit, and inside this they are given a URL. Well, let's say I am here, first page that I've opened is lead code, then it's interview bit. Now from interview bit I want to go to Gmail. Interview bit se pehle I have opened already Facebook, right? Now from I moved back to interview it, and now I want to move to Gmail. So for this, what I will do is I'll firstly take my current pointer, that is IT. This will be pointing to the current. I'll increase the current pointer. Then I'll erase all the pages which are after interview bit, like Facebook and all this. These will be deleted, and then I'll push back my new URL, that is Gmail. So it will become like lead code, interview bit, and Gmail. Then again increase the iterator, and in this way this function is complete. Next, while moving back, these many steps we need to move back, steps minus minus, and until and unless it is not equal to browser page dot begin, we'll keep decreasing this it and we'll return star it. Last function, similar to what we have done in the previous function, we are increasing, we are moving ahead, we are moving in the forward direction. So if we are moving in the forward direction, again we are increasing the iterator, in this case iterator plus plus, and we are returning star it. So I hope this is clear to you. Try implementing this particular problem yourself, you will understand a lot of things. And this is these kind of questions can also be asked in the interview from application point of view, right? So the next question that we're going to discuss is basically LRU cache. So LRU cache, it's a very important question from the point of view of interviews. Like, this is the mostly asked interview question of Amazon. If you haven't heard of this question, so make sure you watch this very seriously. We'll try to demystify what this problem they're trying to say, and then we'll go ahead with the solution part, right? So what they're trying to say is they're saying that you need to design a data structure that follows the constraints of a least recently used cache. So what is cache? We'll discuss about this as well. What we are actually what they actually want us to do is they want us to implement the LRU cache class, and LRU cache, initialize the LRU cache with positive size capacity, then int get, that will return the value of the key if the key exists, otherwise return -1. Update the value of the key if the key exists, otherwise add key value pair to the cache. If the number of keys exceeds the capacity from this operation, evict the least recently used key, right? So this is the question. Let me just try to explain you what they're trying to say, right? So what is a cache, right? It's a form of a memory, right, where we store some databases, right? Consider a situation, you have a large database, right? There are a lot of users, thousands and lakhs and millions of users. So from those users, if at any point you want to search something, so there are million users, if you want to search something from those million users, so it will take time, right? It won't be that efficient, how much efficient sorting algorithm you use, but it will take some time to search from those million or billion of entries, right? So instead of that database, there is a special memory known as cache memory that is maintained, and that contains the elements which are most recently used, the elements which we are using frequently, right? So they are stored in the cache, and it's a smaller memory, smaller space, and searching inside a smaller space becomes easy. Searching inside a smaller space becomes easier. This is very layman terms explanation of what is a cache. If you're not aware of, once you will understand operating systems as a subject, maybe you will or databases as a subject, so you will understand this concept in a more clear and precise way. Now coming upon to our question, right? So what we are trying to say is they have told us to implement least recently used cache algorithm, right? So least recently used cache algorithm. So what actually the question says that, let's say we have database, they have given two functions, int get and int put, right? So from this get function, what they want is, they want key you should search a database and return the value corresponding to the key. Matlab they will give a key here and they want us to return a value corresponding to this key. So this is the function for that. And there's a put function which has key and value as arguments. So this key and value arguments, if we want to add a new entry to our database, right? So let's just look at the function, how it looks like. So yeah, so this is the function that they have given us to complete. This is LRU cache with int capacity as one of the arguments. They want us to complete two functions, int get and void put, right? So first thing is, let's say if we don't consider anything, very simple approach. Let's say we create a map. We all know how to create a map of let's say both integers. I name it as m. To get a function, what I will do is I'll search if m dot find this key is equal to m of n. Well, if this key is not there at all, so what I will do is I'll simply return -1. This is given in the question. Else what I will do is, else I'll return the value that is corresponding to that key. Simple, right? And what will be there in the put? I'll in this m map, I'll put the value corresponding to the key as value, and it's done. So this is something very simple, right? But here we haven't taken care of a lot of things, so let's come on to that. So for solving this particular problem, I will be using the most efficient data structure that can help us solve this problem is a doubly linked list, right? So doubly linked list, it's something of this form, right? You have a node going here, you have a node going here with previous and next pointers, previous and next pointers, previous and next pointers. Let's say this is pointing to null, this is pointing to null. Now this is the database, right? So once any new entry that comes up, we try to add here, right? So this, like in this complete database, this is the most recently used data. This is the most recently used, right? And the data that goes on to the last, this is the least recently used data. Now as soon as we perform any operation, be it get or be it put, right? As soon as I perform a get function or a get operation and a put operation, what I will see is, as soon as I perform a get operation, like I want this particular the value corresponding to this particular data, right? So this particular data becomes my most recently used data. So this should shift to here. So this will become the most recently used. So removing this from here, I will connect this to this and I'll connect this to this directly. And the data which is not used for quite long time, it will automatically reach the end. It will automatically go on to the end. And if at all we put some data, so if we want to add some data, what we'll do is we'll check for the database. If it already exists, what we'll do, we'll erase that data and we'll create a new data and add it in the front. That is, this will be the most recently used. So this is something that we are trying to achieve, and they have given us a capacity, right? So we'll work according to this particular capacity. So let me just try to code in and try to explain you what we are actually going to do, right? So we have already created this map. So let's go ahead with this. I'll create a list of integers, list L. I'll create integer capacity capec I'll create an integer size siz. So capacity and sizes. Capacity is the maximum available database, the maximum available storage capacity, and size is how much is that, how much is it filled at that particular moment, right? So this LRU cache, basically I need to initialize this. So my capac will be equal to capacity, and my size initially will be equal to 0 because there's nothing in the database, right? Now going ahead, now if I want to get something from the database, if I want to get something from the database, first thing is, if I'll make a check. If database doesn't exist, that particular key doesn't exist, I'll simply return -1. So this holds valid here also. But along with that, I can't simply return the key here. What I need to do is, I'm performing a get operation. As soon as I'm performing a get operation, that particular key becomes my most recently used character. So to make that key to the most recently used character, I need to know key which node is corresponding to this particular key. So to get which node is corresponding to this particular key, I'll have to traverse the linked list till this key, so that I can get the address of that particular linked list. Let's say if this is the linked list, right? If I want to remove this particular, I want to get the address corresponding to this key, the key that is present here, right? So as per our understanding, we need to remove this from here and we need to move it here. So to do that, I will need the address of this. How we can get the address of a particular node whose key value we know? Maybe we can create one more map, and inside that map, what we can store is, we can store key value pairs, key and along with their addresses. Like what is the address of this, so that I can simply attach this node here. It will be easier for me to attach this node here. So I'll create another map. So this was map of intended. This will be map of int. And how do we store addresses? We store addresses in the form of pointers, right? But we have already been using iterators. Iterator points to that particular memory address. So we'll be using iterator here as well. Iterator of the form list of integers, and it will be iterator iterator, right? And let me just name it as address, right? So we have created another map from where we can get the corresponding address to a particular key value, right? So that we can simply erase that value, we can remove that value, we can delete that value from its current position, and we can put it in the front, that is, it becomes the most recently used thing, right? Now we have done till here. Now next step would be, I'll calculate the iterator that is corresponding to this key. So to calculate that, I'll do list of integers, and what I was to do, iterator it is equal to address of this key, right? This will be the address that is corresponding to this particular iterator. So this iterator is corresponding to this particular key. So next is, I will erase this entry from my already present linked list. So I'll erase this key. Next, I will erase this key from the address map also. So address dot erase, I'll erase this key. So for removing from linked list, I need to provide the iterator to that particular point rather than providing the key. And also where we need to put it, again we need to put it in the front, because that becomes the most recently used. So what I will do is, I'll do push front key, right? After this, what is to be done? Now new position of address is to be assigned to this key. So new position of address will be address of key equals to L dot start, L dot begin, right? So we'll return M ka key. These steps basically were used to move this remove this key from here and add it here, right? So this is probably our corresponding get function. Now we'll try to see how put function works. What we actually do in put function is we try to create this new key value pair. Like firstly we'll check through this entire list if this key value pair is already present. If it is already present, if it is already present, then I'll erase that, and I'll add new. If it is not present, then I'll add new it, and will add it in the front. Matlab it will again be in l dot begin. So how we can do that? So the first thing that is very important that we will be doing here is firstly checking whether that particular key value pair is already present or not. So I will do that if m dot find key is not equal to m dot end, right? So what I will do is, like, if we find that particular element, we'll erase l dot erase address corresponding to this key, basically the iterator, you can say, right? Next is from that address block also I'll erase this key. Also from the map we'll remove this, right? Because we are trying to, we'll make it one more, we'll make it new. So m dot erase key, and I will reduce the value of size by 1 because we are removing something. ठीक है जी, I hope this is clear. And in the uppercase, why we didn't you do size plus first? Because we are not removing anything, we are just removing it from one side and we are adding it in the front, so size remains the same, right? Now here we have decreased the size. After that, what we are going to do is we want to add that key value pair in the front position, right? So to add that key value pair in the front position, what I will do is l dot push front key, right? I'll also add it in the address of key is equal to l dot begin, because it's the front element of that list. Along with that, m of key is equal to value, right? So this is something that we have already done. Now also the size will increase because we are adding a new entry in the front, so size will be increased. There is still one problem. Let's say if size becomes equal to capacity, then what we should do? If let's say this is the linked list, this is the linked list, this is the most recently used, this is the least recently used, and there is a new entry, there's a new key value pair that you want to add into this particular list or this database or this cache. So what you will do, will you remove this most recently used or this least recently used? So we'll remove this least recently used. Matlab in that particular database we'll remove the last entry. How, when will this condition arrive? This condition will arrive whenever the size is equal to capacity, right? So let me just try to code this as well. So what we will do is, if size is equal to capacity, what we'll do is we'll take the last element of this list, that is, let me store it in k, l dot back, right? Then I'll remove that back element, l dot pop back. Then from address also will erase address, map also will erase address dot erase k. From that m map also will erase m dot erase k, and size minus minus. So if at all size becomes equal to capacity and we still want to add something, so we'll remove the least recently used scenario, right? Let me just try and erase this, and then we'll see what is left now. I hope this thing is clear, right? For most of you, this thing is clear, right? So what we are actually trying to do till here is, Let us just revisit the code and try to see if you have understood or not. Right, so we were to create a we were to implement LRU cache. So you understood what is cache and what is LRU. So now what we say that we create a list that is in the form of a doubly linked list. So STL for doubly linked list is list, right? So this will point to null, this will point to null. So we have LR, we try to implement in this particular fashion, right? Where capex denotes the capacity. That means what can be the capacity of my database. Size denotes the current number of objects, how many we have already added. This is the function where we initialize capacity and size. Initially the capacity is equal to the given capacity, size is equal to 0 because we haven't added anything. Then there are two functions, int get and void put. So what does this int get function means? This function says that I will give a particular key and you return the value corresponding to that key. But once we operate on any key value pair, so let's say this key, our functions call for this key. Once this key is called, you need to return the value corresponding to this key, but we are using this key, right? So this will remove from here and we will be adding it here, because now this becomes the most recent use, abhi we have used, now only we have used. So we need to remove this from here, we need to make this connection as this, we need to make this connection as this, right? And this will be added in the front. Yahan pe we'll add this node. So this becomes the most recently used. So this is only what we have done. So the first step is we try to find that if that number is not present in the list, then we'll simply return -1. Else what we'll do is we create an iterator. Now what we have created, the second thing is we have created a new map, because to get to this particular node, right? How I will reach this particular node, I know the key, right? But I don't know the address of this node, so that I can remove it or I can move this to this to this. So maybe first thing is I need to iterate, I need to traverse over this linked list from 0th position to this position and then get some answer or get some query, but that will be a tiresome process. Instead of that, I've created a map where I've stored the integers and their corresponding addresses in the form of iterators. Now I have this, so I have created this particular iterator, and from this particular map I am getting the value of the address corresponding to this key, right? Now what I will do is I'll try to erase if this is already available, so now we need to erase it. So I'll erase it from this list. Also I'll erase it from this address map, and I will put it in the front. L.push front is equal to key. I'll put it in the front, right? Then address of key address of key also changes. If I put it here, so what will be its new address? Its new address will be corresponding to the address that is L.begin, and I will return the value corresponding to it. I hope now it is a little more better, right? Cool. So the next thing is a put, right? So put functions tells us to add a new key value pair. So if I want to add a new key value pair, like this is the current structure that we have. This is the current structure that we have, and they tell us to add a new key value pair. So where we'll add the new key value pair, we'll add it in the front for sure, right? But before that, before doing this, I will check whether this key value pair is already present or not. If at all this key value pair is present, so I will erase that key value pair, right? And then only I will add this. So this particular thing we are doing it for finding and erasing that particular key value pair from my already available database. If at all this does not work, well, this erases that particular key value pair from my already available linked list, and after that I try to push my key value pair in the front, and address corresponding to begin is mentioned, and we assign that key value the correct pair. right? But still one problem is there. If at all the size becomes equal to capacity, if at all the size becomes equal to capacity, then what I'm going to do is, from this linked list, this is the most recently used, I know this is the most recently used, and this is the least recently used. So which one I should remove? Should I remove the most recently used, or should I remove the least recently used? Obviously this is something that we are not using from quite some time, so I will be removing this. So here also what I have taken is, I have taken the last element, I have removed that last element, erased that from the address, and size I have decreased. So this is what is being done, right? I hope things are clear to you now. So what I want you to do is try to dry run this particular question, because some of you might face difficulties in understanding it for the very first time if you're doing it for the very first time, right? Make sure you try to dry run it on your own on a piece of paper, right? After that, try to submit your code on platform and try to analyze what is its time complexity and space complexity. You can do comment the time complexity and space complexity if you are doing this question on your own. I'll try to reply to all the comments that you do on this video, right? Now I hope this question is clear. If you still have doubts, make sure you ping your doubts in the comment section. I'll be more than happy to take it from there, right? Moving on to the next question. So the next question that we're going to discuss is basically a palindrome linked list. So you might have heard this term before also. What is a palindrome number, right? Palindrome number is such that, let's say we have 1, 2, 1, 1, right? You read it from the front, you read it from the back, it is one and the same thing, right? 1, 2, 3, 2, 1. It is also a palindrome number. And you might have also done this question in arrays or vectors, right? You are given an array and you need to check whether this is a palindrome array or not. Let's say if an array has these numbers 1, 2, 3, 4, 3, 2, 1. So this is a palindromic array, right? So you need to check and return whether it's true or false. That means the array is palindrome or not, right? So you have done this in arrays. How we do it in arrays? We use two pointers approach. We take a pointer, a left pointer here, we take a right pointer here, and we start comparing left and right. As soon as any of them mismatches, we return false, else we return true. So this is a very efficient and a good approach. But now the case is not like that. We are given a linked list, right? We are given a linked list of this particular form. Let's say 1, 2, 3, 2, 1, null. So this is the linked list that is given to us, and we need to return whether this linked list is palindromic or not, right? So how can this be done? The first way that comes to your mind may be, let's say I convert this linked list in the form of arrays or vectors, and I use two pointer approach. But in this case, there will be a lot of space complexity involved again. So we'll avoid this, we'll not use this space complexity wali cheese. Instead, there is something else. Like what can be done is, let's say we have this linked list, right? 1, 2, 3, 4, 3, 2, 1, and null. Let's say we have this linked list, right? So what we can do is, maybe we can divide the linked list into two parts. This is one part and this is another part, right? Or we can have we can divide the linked list into two parts and reverse the second part. So this becomes something like 1, 2, 3, 4. If we reverse, 1 will come here, 1, 2, 3. So we'll make a pointer here, we'll keep a pointer here, and we'll start comparing. 1 is equal to 1, true. 2 is equal to 2, true. 3 is equal to 3, true. So this is what I can say is a palindromic linked list, right? This can be one way. So, and let's say this is for the case when the number of elements are odd. Let's say we are doing it for when the number of elements are even, right? 1, 2, 3, 3, 2, 1, right? So for this we'll divide it from here. We'll have it like this: 1, 2, 3. We'll reverse this list. We'll get 1, 2, 3 again, and then we'll compare both of these. Take a start pointer, take a mid pointer. We'll move start pointer one step, mid pointer by one step, and compare at each point. As soon as any of these mismatches, what we'll do is we will return false, else we'll return true, right? And make sure, like, if the elements are odd, then we need to return the middle. We need to find out the middle and then reverse the next linked list. Matlab, an element prior to the middle we need to find, right? And similarly in even case also we need to find the first middle, and the rest linked list is to be reversed, right? Let's just move on to the code and see if we are able to code this particular problem. Then you will be able to understand it a little more better way, right? So let's say this is a problem, right? So this is the problem that is given to us. We are given the head of a singly linked list. We need to return true if it is palindrome or not, right? So this is the head that is given to us. We need to check if it is palindrome. So the first thing that we will be doing in this particular question is we'll be finding out the middle and then reversing the middle. So how we generally find out the middle of a linked list? Using slow and fast pointers. We move slow pointer by one step, fast pointer by two steps. We've already done this question in the previous portion of this video, right? So what I will do is I will initialize a list node star slow is equal to head, list node star fast is equal to head, right? While fast का next is not equal to null and fast के next का next is not equal to null. Why I'm doing this? Because I want the first middle element. Try to try run this and you will get the answer of this. Why fast ka next is not equal to null and fast ka next is not equal to null. Earlier we were doing fast while fast is not equal to null and fast ka next is not equal to null. Now we have changed the condition because we want the first middle, right? Slow will be equal to slow ka next, fast will be equal to fast ke next ka next, right? So both of these are done. After that what we are trying to do is slow. Now we have got, now the slow pointer carries the middle element and after slow ka next we need to reverse. So how we reverse a linked list? We have already written the code for reverse a linked list. I'll just copy paste this same reverse the linked list code and I'll use it in this particular problem, right? So what I can do is I can simply say slow ke next mein what you can put is reverse list starting from slow ka next, right? Reverse list true. So now we have half linked list as straight and half linked list as reversed, right? Now what we need to do is we need to compare. How we'll be comparing these two linked lists is we'll have two pointers. One is again a a start pointer, one is again a mid pointer, and we'll compare both of them. How we can compare both of them is let's say I take a new node, list node star start is equal to head, list node star mid is equal to slow ka next, right? While mid is not equal to null, what I will do is, if mid value is not equal to start value, will return false, right? At any point if this doesn't happen, will return false, and we'll move start equals to start ka next and mid equals to mid ka next, right? And we'll simply return true after that. After moving coming out of the linked list, we'll remove return true. That means the linked list is a palindromic linked list, right? Try to submit. Yeah, so we have successfully, has been successfully implemented, right? So what we are doing in this particular question is, I hope you can understand it now with the help of code as well. So let's say we have this, now it is better. 1 2 3 3 2 1. So what we did here is, we took a slow pointer, we took a fast pointer, both keeping here fast pointer, and we tried to move when it in a while loop until fast ka next is not equal to null and fast ka next is not equal to null, so that as soon as my slow reaches here, I get the mid of my linked list. Now what I've done is, in slow ka next, after this I am attaching reverse list slow ka next. This entire list is what I am passing out in the reverse function, and this list becomes something like this. This becomes my new list. Now this becomes my new list. It is 1 2 3 1 2 3 and null. This becomes my new list. Now what I did was, I made a start pointer that was pointing to head. I made a mid pointer that was pointing to slow ka next, that is this. Now I start comparing mid key value with start key value. This value is being compared with this. Yes, if at any point they don't match, this is not matching this, this is not matching this, this is not matching this, I'll return false and I'll keep on moving. Else, if this comes out from this loop, we'll return true. So this is how we check whether a linked list is palindrome or not. I hope this question is also clear. It's also one of the important questions, you can say, from the point of view of linked list. So make sure you do it on your own once. And let me know if you have any confusions, any doubts. Please type it down in the chat box, in the comment section. I'll be more than happy to take all your queries, right? So the next problem that we're going to see is basically intersection of two linked lists. What we are given in this particular question is, you are given the heads of two singly linked lists, head A and head B. You need to return the node at which the two lists intersect. If the two linked lists have no intersection at all, then we can return null. For example, the following two linked lists begin to intersect at node, like we are given A1, A2, B1, B2, B3, C1, C2, C3. So we need to know the intersection point of both these linked lists. We have been given two linked lists with head A and head B, right? Let's just see how what can be the approach. So the question, the lead code example was A1, A2, C1, C2, C3, null. Here it was, I guess, B1, B2, B3, right? So this was the problem that was given on lead code, and they wanted us to get the intersection of linked lists, right? So this is the intersection point and we need to return this, know this, right? So what can be the first way? What can be the brute force approach, right? Maybe I'll choose this one and I'll traverse B, linked list B, right? I'll move from B1 to B2 and I'll match it with A1, whether it is matching or not. I'll move from B1, B2, B3, C1, C2, C3. If at no point they don't meet at any point, so I'll move to A2. Then I'll check match with every node of B, whether it is matching or not. If it is not matching, we'll move to this Now in this case, if we'll traverse the linked list B, so they both will match, hence will return true or will return this node. But this will take the time complexity of O of m into n. If m is the length of this this linked list and n is the length of this linked list, then O of m into n time complexity, which is very, very expensive, right? So we'll not prefer this. Instead, what can be done is, let's say there's a set, set data structure, right? Set in SQL we have seen. So what we can do is, for one linked list, we traverse and put all the nodes in a set, unordered set or map, you can say. And like A1 will be here, A2 will be here, C1 will be here, C2 will be here, C3 will be here, and so on. Now we'll start traversing linked list B and we'll see if B1 is already present in set or not, B2 is present in set or not, B3 is present in set or not, C1 is present in set or not. We have significantly improved upon our complexity, but again we are using an extra data structure that can be a problem at any point. So what can be a little more better approach? Let's discuss once again, like, what is the solution. A1, A2, C1, C2, C3, null. In this case it is B1, B2, B3, right? These are the two linked lists. Now the next thing that I want to do is, what I will do is, I'll calculate the length of both, length of A and length of B. Now length of A is 1, 2, 3, 4, 5. Length of A is 5. Length of B is 1, 2, 3, 4, 5, 6. Length of B is 6. Now to make them both move in a synchronized fashion, what I will do is, I'll traverse the longer one. Well, I'll take the difference of both the nodes, 1, and I'll traverse the longer one by the difference, right? So I'll traverse it till here. So this is the starting point. Now I'll move both of the linked list from here. They'll see if they're equal, no. If they are equal, no. At this point they meet each other. So this synchronization can help us in understanding that how we can improve the time complexity. Now this synchronization concept, if we try to implement in one more way, how can that be done? Right, let's say I have this linked list again, A1, A2, C1, C2, C3 and null. Here it is B1, B2, B3 and so on, right? So let's say this is list 1, this is list 2, right? I start from this list, A1 starts from this list, list 2 starts from this. Let me just consider this distance as hypothetical x, this distance is hypothetical y, this distance is hypothetical z, right? So total distance that list 1 covers is x plus y, total distance that list 2 covers is z plus y, right? Let's say I want them to cover the distance of both of these linked lists. Like list 1 covers first x plus y, then it covers z plus y. Similarly, list 2 covers its own distance z plus y, then it covers list 1's distance, that is x plus y. So again, these both distances become equal, or they are in sync, I can say. As soon as they are in sync, we'll traverse, I'll traverse list 1 from A1 to A2 to C1, C2, C3. As soon as it reaches null, I'll start traversing it from this side, B1, B2, B3, C1, C2, C3. So what happens in this case is, they both will be in sync at this point. They both will meet at this point and we don't need to do anything. This is the best possible solution that is available. Let's just try to dry run and see if this works, right? Let me just use an eraser. Okay, so what I tried to say was, like, A is here, B is here, right? A moves to this, B moves to this, A moves to this, B moves to this, A moves to this, B moves to this, A moves to this, B moves to this. Now after this, A moves to this and B moves to this. A moves to this, B moves to this. Now they both are in sync again, right? They both are at the same place. Now B moves to this, A moves to this, B moves to this, A moves to this. Now again both B and A are equal. As soon as they are equal, we got our point. Well, this is something that we wanted to know in this particular question. So this is the approach, this is the best approach that you should give to the interviewer once, like if this particular question is asked to you in an interview, right? So let's see how this code works, how we can code this particular approach. So yeah, so the first thing that you should do is list node star, let's say A is equal to head of A, star B is equal to head of B. So I have two nodes A and B. I'll run a loop until A is not equal to B. While A is not equal to B, what I will do is the point at which A equals to B, so that means that is the intersection point, right? So we'll run this loop until and unless A is not equal to B. So I'll see if at all A is equal to null. A becomes null, then A should point to head of B, right? We'll start traversing from B if A equals to null, else A equals to A connects, the A moves forward. Similar is the case with B. What we'll do in case of B, if B equals to null, B equals to head of A, else B equals to B connects, right? So as soon as they come out of this loop, we can return A. Let me just try and run this code if this works. Okay, so there is a declaration problem. Let's just run this again. Yeah, so both of them are intersecting at 8, so we have got the correct output and it has been accepted. So what we are doing in this particular case is, let me just explain it to you again. So let's say we have this particular linked list 1 2 3 4 5. Here I have 6 7 8 and this null. So I need to tell at which point they intersect. Now this is list 1, this is list 2, right? I make it point to as A, this I make it point to as B. Now I check for if A is not equal to B, if at all A is not equal to B. So if A is not equal to B, I'll see if A equals to null. No, A is not equal to null, then I'll move A forward. Similarly, I'll see if B equal to null. No, B is not equal to null. I'll move B forward, and we'll do this until both of them are at the same position. A is here, B goes here, A is here, B goes here, A is here, B goes here, A is here. Now A becomes null, so B goes here. As soon as A is equal to null, we move it to B. Now it starts from head of B. So now A is here, B goes to null, A is here, B goes here. Now both A and B are in sync, right? So as soon as they are in sync, now again we'll start moving. B is here, A is here. Now B is here, A is here. B and A both match at this point. We'll simply return A, or we can say we return B. As soon as they become equal, so they'll move out of this while loop and we'll return the answer. So this is what we are doing in this problem. I hope you are amazed by the solution, and if you have any doubts still, so do comment in the comment box. I'll be more than happy to take all your queries, right? Now let's move on to the next problem. So the next question that we're going to discuss is basically a partition list. Now let's read the problem first and see what they're trying to say. Given a head of the linked list and a value x, partition it in such a way that all the nodes less than x comes before the nodes that are greater than or equal to x. you should preserve the original relative order of the nodes in each of the two partitions. This line is very important. So what they're trying to say is, like, this is the example given in which we have linked list with nodes as 1, 4, 3, 2, 5 and 2, and they have given us the value of x as 3. All the nodes which are less than 3 should come at the front, and rest of the nodes should be after that. So how we'll be doing that? uh, like, what exactly they want is, like, the number given is 3, so 1 is less than 3, yes, 1 is here. 4 is not less than 3, will not take it. 3 is not less than 3, will not take it. 2 is less than 3, so 2 is here. 5 is not less than 3, 2 is less than 3, then 2 is here. So we have all the numbers which are less than 3 as the first elements, and after that, maintaining the relative order of the nodes, like 4, 3 and 5, we have 4, 3 and 5 here. So we need to solve this problem. Let's just discuss the approach on how we can think upon this particular problem and how we can come to the solution after that, right? So yeah, so the question that we are going to discuss now is partition list. So the question name is partition list. What you are given in this particular problem is, you are given, let's say, 1, 3, 5, 7. Let's take another example, right? Let's take an example 7, 5, 9, 1, 8, 3, right? So x value that is given is 4. So for all the nodes which are less than 4 should come in the front, and all the nodes which are greater than 4 should come at the end, right? So we'll start comparing the first node with 4. Is it greater than or less than? No, it is not. It is greater than, right? So it should come in the end wala node. 7 should come here. We'll compare 5. 5 is also greater, so 5 should come here. Next is 9. 9 is also greater, so 9 should come here. 1 is smaller, so 1 should come here. 8 is greater, so 8 should come here. 3 is smaller, so 3 should come here, right? So our output should look something like this: 1, 3, 7, 5, 9 and 8. And you can see this order is preserved, like 7 ke baad we get 5, ke baad we get 9, ke baad we get 8. So this order is very important. We need to maintain this order only. So this is a very peculiar approach that we are going to solve this question with. Let's say the same question I have: 6, 5, 3, 1, 2, 9 and null, and I am given value of x is equal to 3. What I will do is, I'll create a dummy node by the name of left, I'll create a dummy node by the name of right, and I'll start traversing this linked list from the head pointer until head becomes null. I'll compare this with the value of x. If it is greater than the value of x, I'll put it in my right list. If it is greater than, I'll put it in my right list. If it is smaller than, I'll put it in my left list. 1 is smaller, I'll put it in my left list. 2 is smaller, I'll put it in my left list. 9 is greater, I'll put it in my right list. Now once I have the left and the right lists, I'll combine both of them, right? And here, along with that, we'll maintain a tail pointer that will move to the last pointer, because we need this at the end, because once we need to join this along with this, so this tail of left should join to right. Tail of left ka next should be equal to the right, because we need to combine both of them together, and the tail of right should point to null. So we need to do this at the end after creating a left and the right list, right? So once we'll code it, I think you will be able to understand it better, right? So this is the problem statement that is given to us. We are given the head node and we are given a value x. So we'll be this value of x decides ki the number of nodes should, how many number of nodes should be present in the front. So we'll create two list nodes. List node star left equals to new of list node. Let's say we start it with -1. We create another node, list node -1 again. Let me just name it as right, and also we'll maintain their tail pointer so that we can easily connect both of them after we make them. List node star l tail, list node star r tail. Initially l tail is pointing to left and r tail is pointing to right. ठीक है जी. So L tail and R tail are done. So I'll move while my head is not equal to null, and I'll compare the values of x with the head key values. If head key value is less than x, then what I will do is I'll put that term in the left wali linked list with the dummy pointer. So L tail का next will become equals to head, and L tail equals to L tail का next, but the L tail moves forward, right? What will come in the else part? Else, if this is not the case, R tail का next will become equal to head, and R tail equals to R tail का next. So both our L tail and R tail are made, right? And we'll be moving our head forward, like we'll traverse the entire linked list. Head is equal to head ka next, right? After this is done, at the end what we need to do is R tail ka next should be equal to null, because R tail is the second list ka next is equal to null, and L tail ka next should be equal to the right pointer, मतलब जो dummy pointer है उसका next, right? At the end what will return is left ka next. Why left ka next? Because left is containing a dummy pointer. We don't need to return that dummy pointer of -1. Dummy pointer के आगे वाला number is what we are going to return. Let me just try and run this program and see how it goes. Okay, there is a spelling mistake. Yeah, so we have successfully solved this problem, and the solution has been accepted also. So this was it. Let me just dry run through it once again. So what they have given us, this example: 1 4 3 2 5 2 and null, right? And they have given the value of x as 3. What we are doing is we have created a left dummy node and we have created a right dummy node. So I am moving it inside this while loop until and unless this head is not equal to null. Like this is currently head, and I keep on traversing this linked list. If head key value is less than x, मतलब 1 is less than x, right? Then what I'll do is I'll join it in front of my left tail, and tail moves forward. This is L tail. Now 4 is greater than 3, so if it is greater than 3 we'll move on to the else part. 4 is joined here, and this is R tail. Again 3 is there, 3, whether it should be less than 3, strictly less than 3, so it will come in the R tail. R tail will move here. 2 will come in the L tail. L tail will come here. 5 will come in the R tail. R tail will come here. 2 will come in the L tail. L tail will come here, and it reaches null. We'll do it until and unless head does not reach head equals to null, right? So now we have two separate linked lists, left and right. What I need to do is I need to make this L tails next point to right ka next. This should point to this. This is what I am doing here. And R tail ka next to be null. R tail ka next is to be pointing to null. So my linked list will finally become 1 2 2 4 3 5 and null, and this is pointing to left, left dummy node. So at the end, what I will return? Left ka next. I'll start returning from this, and this is the answer that we'll get. Right? I hope this is clear. I hope you are able to solve this particular problem. Right? Now moving ahead, there is something known as circular linked list. I'll not go into the depth of circular linked list. That is something that you can explore upon. There are some problems that can be solved using a circular linked list, but if you have understood the concepts of singly linked list, then circular linked list is not a tough topic. It's completely almost similar. Just some things you need to understand. Just from basic point of view, if I talk about what is a circular linked list, right? What is a circular linked list? So our singly linked list is something of this particular sort, right? We have nodes, this, let's say data is 1 2 3 4, address of this is 100, this is 200, this is 300, this is 400. This stores the address of next, it is 200, it is 300, it is 400, and it is null. This is my singly linked list. What happens in a doubly linked list? We have discussed doubly linked list as well. तो doubly linked list में क्या होता है? Doubly linked list में the picture is something like this. Now you can visualize it something like this. This is pointing to null, this is pointing to null. They have two pointers, previous and next. Previous and next. Let's say the address of this is 100, 200, 300, 400. So this will store 200 here, the address of the next. This will store the address of the previous here and the address of the next here. This will store the address of the previous here, address of the next here. This will store the address of the previous here, address of the next here. These are the datas 1, 2, 3, 4, and this was something known as a doubly linked list. Now what is the difference between what is a circular linked list? So it is similar to singly linked list. So what happens in a circular linked list is we have 1, 2, 3, 4, 5. This was singly linked list. So now instead of 5 pointing to null, if 5 points back to 1, right? There's no option of null in a circular linked list. Like there's no node that is pointing to null in a circular linked list. Like there is a head pointer that points to the start node. There is a tail pointer that points to the tail node, right? And tail, every time tail ka next is equal to head. So this is the condition for circular linked list, right? If you want to insert a new node in a circular linked list, what you will do is, you will store the address of the head. You know already the address of the head. You will make a new node, let's say 6. You will make tail ka next point to 6, and 6 becomes the tail, and tail ka next points to head again. This is what you will be doing, right? If you want to insert a new node. Similarly, you can perform all the operations that we have already done on different types of linked lists, like insertion, deletion, searching. So all these operations can be performed on circular linked list as well, right? I want you all to try circular linked list on your own once. If you feel like solving problems on circular linked list is difficult, do let me know in the comment section. I will come up with a separate video for circular linked list as well, right? So that was all about linked list as a topic. We have extensively covered a lot of topics, and I believe you would have understood a lot of them, right? So from the point of view of understanding of linked list, now I believe all these things are clear to you. We have started with representation of a linked list, right? We've started with the which all topics we have covered in linked list. So we have started with the need for linked list, advantage over arrays, then we discussed about representation of a linked list, like printing linked list. We saw insertion, deletion, searching, size of a linked list. We found out the middle of the linked list. We did some different problems on lead code on different other platforms. We solved problems like cycle detection, that was done using Floyd-Warshall algorithm. We did problems related to palindrome number, palindrome linked list. We did problems related to LRU cache. We did problems related to different other problems. We also discussed a doubly linked list, structure of doubly linked list. STL in linked list. Along with that, some more topics we have discussed. So this covers all your fundamental concepts of linked list. Now what I advise you to do is, once you have watched this video till the end, go to any of the sites, be it interview bit, be it lead code, or any other site that you want, and try practicing some random questions based upon linked list. Now I feel that you are ready for this topic and you can solve all the problems, be it from easy category, medium category, or hard category. So make sure you utilize your time well and practice more questions. It's not just about viewing these videos, it's more about practicing a lot of questions. That is ultimately going to help us in the longer run. So make sure you watch this video. If some concepts are not clear, do comment in the comment box. If concepts are clear, make sure you hit the like button and subscribe to this channel as well. And let me know which all more tutorials you're looking forward to in the series. I'll come up with the complete tutorials on any of the topics that you are looking forward to, that you are facing problems in currently. So this was all for this particular video. I thank you all for keeping the patience and being till here till the end of this video. This was amazing to teach all of you the concepts of linked list. Soon some more videos are going to be uploaded on this channel as well. Till then, all the best, see you.